Hey everyone. Hopefully everyone can hear me out there. This is the first time I've tried to live stream, so I'm sure there'll be a couple hiccups along the way, but we'll make the best of it, I'm sure. So just a couple quick things before we get started. The first thing is I do have the chat stream open. That's for any questions that you guys might want to pose to me. Now I can't uh, do the examples and look at the chat at the same time, so I'll do my best. But let's keep the chat sane, and let's keep everything civil in the chat area, and let's get started. Just a couple things before we get into the examples and the notes. Is first, I can't possibly cover all the topics we covered in the course. There are 36 course hours, and this will only be 12 hours of review, so this certainly does not replace studying. So just because you are here doesn't mean you probably know everything, so you should probably study even after this. The best way to study for the course would be to do and understand as many problems as you can find. So your textbook, certainly. Any other textbooks, there's lots of textbooks in the library on first year calculus, any past exams, Google some questions. Anything you can possibly get your hands on, you should probably try and understand. The problems in these review sessions are generally a little bit more difficult than you've seen in lecture. So lecture is usually the first kind of introductory examples to some of the topics, but these review topics is going to be these review questions are all going to be a little bit more challenging, so hopefully everyone can follow along. There may be typos in some of these notes. That's okay. As always, your best bet, if you think that there's a typo in a formula or something that I presented, best idea is to check the textbook. The textbook has all of its typos corrected, so that's your best bet as far as memorization of formulas. And I won't be able to do a question for every single topic that I cover. We will do a lot of questions. Hopefully we can get through all of them. I'm not sure if we'll be able to get through all of them, but I'll go as quickly as I can. I'll try to do as many questions as I possibly can. So probably the best idea for you to think of this review is to look at the stuff that I've covered, look at the stuff that I've talked about. Hopefully it'll refresh your memory on stuff that you haven't maybe looked at while you were studying, and maybe you want to go back and double check some of those examples. So once again, I can't cover everything. I won't be able to get to all the questions, but you still have about a day and a half to study. So this should serve as a general review and just some indications as maybe what you might need to cover over the next day and a half. Okay, so let's get started. So simple stuff first. So functions. So we've seen lots of functions. This whole course is about functions. And the first thing we probably talked about are one-to-one functions. One-to-one functions are any kinds of functions that have this property. So if you have a one-to-one function, if you plug in, say, x1 into a function, and it's not equal to x2, that must happen whenever x2 is not equal to x1. When can we usually check this? We can check this when we have a function and we can graph it, like we can graph it here. Let me see if I can get my pencil. Let me see. Okay, if you want to check to see if a function is one-to-one, you can do it algebraically, but that's a little bit outside the scope of this course. So usually what we do in this course is if we have a nice curve of the function, so for example here, we see that this function, we graph it, this is y equals f of x. And if we draw any horizontal line and that line crosses the function in more than one place, so for example here crosses the function in two places, this is not one-to-one. So whenever you can draw any horizontal line through a not one-to-one, not one-to-one. So anytime you can draw a horizontal line like this through any function and it crosses the function in two places, you say that it's not one-to-one. This is how we generally check one-to-one functions. Inverse functions. So why would we care about whether or not a function is one-to-one? Well, whenever a function is one-to-one, we can then say that there definitely exists. We don't know necessarily what it is, but we can say it exists. There's a unique function that's called the inverse function. We usually denote it f to the -1. Something I want to point out here is I agree this is very bad notation. This is not 1 over f. Okay, this just means the inverse of f. And the way that the inverse function is defined, it's defined to be this. If you take a y value and you plug it into your inverse function, you'll get x out. And this happens if and only if the value of your function when you plug in x is equal to y. So essentially the inverse of a function is just a function in reverse, so it undoes a function. And we can classify that mathematically by these equations here. These are called the cancellation functions. It looks overly mathematical, but essentially you guys have all seen this before, and that is if you take the function of the inverse of a function at x, you get back x, and the reverse. So for example, let me give you a quick little example. If our f of x is equal to sine x, so if this is our function, you guys have all seen this before. The inverse function we've all seen. It's the inverse sine, or I like to call it arc sine, just so that the notation is clear. So what this means is, if I take f of x, f of the inverse of x, well, what does that look like? That just looks like, for us, sine, because sine is the function, of arc sine x. And the way most people like to think of it, although it's not quite mathematically true, but most people like to think of this is that sine cancels out with the arc sine, and what you get at the end of the day is just x back. So this is the way the cancellation formulas work. And it works in the exact opposite way as well. If you took the arc sine of sine of x, you would get back x as well. So this is what these cancellation equations mean. You guys have all seen them before. Maybe you didn't know that you were using them, but this is the idea behind the cancellation equations. Okay, so perhaps you're asked to find an inverse or to sketch an inverse. You don't always have to find the inverse before you sketch it. For example, if you were given a nice function here, so this nice blue function is your function. If you sketched it and it looked like this, for example, you wouldn't necessarily have to find the inverse of the function before sketching it. What you could do instead is you could just reflect it over the line y equals x. So here's the line y equals x, and if you just wanted to graph the inverse of this function, you just reflect it. So that's all it would take. You wouldn't have to figure out what the actual function was and then go ahead and do all the sketching stuff. You could just reflect it over y equals x, and that is the graph of the inverse. Okay. So that's about inverse functions. And then algebraically, I'm sure everyone's done an example like this. How do you find the inverse of a function? If you would like to find the inverse of a function, for example, if you had a function f of x is equal to, say, 3x minus 6. If this was your function, how do you find the inverse of this function? Well, the first thing you do is you replace f of x with y. So I say y equals 3x minus 6. And then I interchange x and y, so I say x is equal to 3y minus 6. So wherever I saw an x, I plug in a y. Wherever I saw y, I plug in an x. And then I isolate for y if possible. So if I isolate for y here, I get negative 3y equals negative x minus 6. And then if I divide both sides by negative 3, I get y equals x plus 6 over 3. And then at the end of the day, I replace y with the inverse. So f negative x, f inverse of x is x plus 6 over 3. So you guys have done lots of examples like that. So that's generally how you find the inverse of a function. Okay, so now on to the real stuff. This is when most of the real interesting stuff happens for the course. Let's start talking about limits. So for us, the definition of a limit is, the idea of a limit is whenever we have a function f of x, and as long as it's kind of defined near a point, so we want to make sure that x is kind of defined near x equals a, so nothing kind of weird happens. Then we say that the limit of f of x as x goes to a is equal to L. What that means is as x gets closer and closer to a, f of x gets closer and closer to L. So the y values you're getting out of your function are getting closer and closer to L as x gets closer and closer to a. This is our idea of a limit. The reason I have the limit in quotation mark, or the definition in quotation marks up here is technically you want to start defining limits in terms of epsilon and deltas. Maybe you've seen that before. Maybe some of your math colleagues have seen it before. That's outside of the scope of this course. So for us, this serves as a nice definition for a limit. So the main methods to calculating limits, you know 4 of them. The first one is direct substitution. So this is you just plug in a. Usually you won't have a question like this. It's far too easy, I think, for this course. So you're probably going to see most of these types of things: factor and cancel, rationalization, and the squeeze theorem. These are going to be the ones that you do to calculate limits. Just to remind you what the squeeze theorem is, once you see a picture of it, it's kind of easy to understand. If I have a function f of x, and the function f of x is always smaller than a different function g of x, and that function is always smaller than h of x, at least when x is near a, and I know the limit of the smaller one is equal to L, and I know the limit of the bigger one is equal to L, well, g of x is in between these two things, so the limit of g of x then also has to be equal to L. So this is the squeeze theorem. Here's what it looks like graphically. So here is the function that's always bigger than the rest, so this is h of x. Here is always the function that is always smaller than the other functions. This is f of x, and here is the function that we're interested in. This is the one that's getting squeezed in between, and you can see as x gets closer and closer to a, what's happening? Well, our big function is getting closer and closer to L. Our bottom function is getting closer and closer to L. Therefore, the function that we're actually interested in, this one in between, it also has to get squeezed in between the top function and the bottom function, so its limit also goes to L. This is generally how the squeeze theorem works. The limit laws, there are lots of them, but I'm sure everybody has used them before, even if you didn't know that you were using them. For example, if you have two functions, f of x and g of x, and you add them together, you can take their limit. Instead of putting them together, what you can do is you can do them separately, and this is only true. You can only do this if these two limits exist. Okay, we'll see a little question about this in a little bit. But you can only separate this stuff if it makes sense to separate it. If you can actually separate, if these two limits actually end up being a number, then it's okay to separate it. If one of these two things does not exist, you're not allowed to separate things. Same for differences. So if you take f of x minus g of x, you can split them up as long as these two limits exist. If you have a constant multiple, you can always just pull that outside of the limit and just concentrate on the limit of f of x instead. If you have a product, so you have f of x times g of x, you have two functions multiplying each other. Rather than do the limit of their product, you can do the limits individually. So you can do them separately and then multiply them together, provided these two limits exist. If these two limits don't exist, then you can't do this split. Same with dividing. If you have a function f of x divided by g of x, it's totally okay to look at the limit of the top divided by the limit of the bottom. Again, this only is true if this and this exist, and because we never want a denominator to be 0, we also can't do this if this is happening. If the bottom is actually going to 0, we can't do it this way. We also have a power. You can put the limit inside of a power if you want, provided this limit actually exists. And same with a fractional power, so any kinds of square roots or anything. So these are the limit laws. You guys have used them before, even though you didn't know you were really using them. A couple important trigonometric limits that you might want to memorize because you might need to use in a calculation is that the limit as x goes to 0 of sine x over x equals 1, and the limit as x goes to 0 of cos x minus 1 over x is equal to 0. Okay, so those are some important limits, and we'll talk about one-sided limits in a second. Let's look at some examples first. Let's do some examples. Okay, so here's a typical limit question. Let's look at the limit as t goes to -3 of this function here. So like I mentioned, there are really only 4 methods that you know before we get to L'Hopital's rule. There's only 4 methods you know to actually calculate this limit. The first would just be to plug in t equals -3 into everything, but if you actually try to do that, what you would find is that the denominator goes to 0, so we don't really want that. So we're going to try a different approach. The approach that's going to work in this case is going to be factoring. So if you look at this, this is actually a nice little factoring problem. So this is equal to, for example, the limit as t goes to -3 of the top factors into t minus 3 times t plus 3, and the bottom's going to take a little bit of work. What we're going to look for is two numbers that multiply to be 6 and add to be 7. So two numbers that multiply to be 6 and add to be 7 are 6 and 1. So we're going to separate this into 2t plus 2t squared, sorry, plus 6t plus t plus 3. So we're just separating that 7t into 6t plus t. Why do we do that? Well, that means we can rewrite the bottom as, well, the top is t minus 3, t plus 3, and the bottom, then we can factor out a 2t out of the first term, and this now becomes t plus 3. And the bottom, or the second term, is also t plus 3. So that's why we divided it up the way we did. If we continue right along, this is limit as t goes to negative 3 of t minus 3. I think that you can all see where this is going. So the final factorization of the bottom is now 2t plus 1, t plus 3. And now we're in a position that we can actually cancel out the t plus 3's from the top and the bottom, which is good because this t plus 3, this factor here, is what was actually causing us all the problems when we tried to plug in t minus 3. So now we're just left with the limit question. Limit as t goes to negative 3 of t minus 3 over 2t plus 1. And if we plug in negative 3 to all of this, we get, this is going to be negative 6 divided by 2 times negative 3 plus 1, which is equal to negative 6 over negative 5, which is equal to 6 over 5. Okay, so that's an example of factoring to solve your limit problem. So let's move on to another example. So here's an example where we have some square roots. Usually, square roots are a big hint that you want to multiply, you want to rationalize some things. So you want to multiply by the conjugate. So what we want to do here is we want to rewrite this as the limit as t goes to 0 of square root of t minus 1 minus the square root of, square root of square root of t1, square root of 1 plus t minus the square root of 1 minus t over t. And what we want to do is we want to multiply the top and the bottom by the conjugate of this. Now the conjugate of this is uglier than probably some of the examples you've seen before. This is 1 plus t and square root plus, so the opposite sign of this, the square root of 1 minus t. And we, in order to not change the question, obviously, we want to multiply the top and the bottom by the same thing. So we're going to multiply by 1, or divide by 1 plus t plus the square root of 1 minus t. Okay, so that's the idea behind these questions. We want to multiply by the conjugate. So let's continue on and let's just actually multiply all this out. So the reason that you want to multiply by the conjugate is because when you actually take multiply these square roots, the square roots actually end up going away. So this ends up being, the top is going to be 1 plus t minus 1 minus t. So that's what we're going to get on the top once we carry out that expansion. And in the bottom, I'm just going to leave as t times the square root of 1 plus t plus the square root of 1 minus t. Okay, I'm not going to bother expanding that out. It makes my life more difficult, so I'm just going to leave it like that. Okay, so let's simplify the top now. The limit as t goes to 0 of 1 minus 1 is 0, and t minus minus t is 2t. And now the bottom is t plus all this nonsense that we have in here, 1 plus t plus square root of 1 minus t. Okay, so that's all on the bottom. And now we get this nice cancellation that we wanted. We get this t canceling out with this t, which now gets rid of our problem when we just want to plug in t. So this ends up being the limit as t goes to 0 of 2 on the top divided by square root of 1 plus t plus the square root of 1 minus t. So now we can plug in t equals 0 because there is no problem. And when we plug in t equals 0, we get 2 over 1 plus 1, which is equal to 2 over 2, which is just 1. Okay, so here's an example where you want to use this conjugate whenever you have things that look like square roots. Is usually a good idea. Whenever you have a square root minus square root, or whenever you're doing something that involves square roots and you're adding and subtracting something, that's usually when you want to use the conjugate. Okay? All right, so here's another question. So what we would like to do is we would like to find the limit as x goes to 4 of f of x, where f of x is in between this function and this function. So this looks like a classic squeeze theorem question. So let's take a look at this. Limit as x goes to 4 of this function on the right, or on the left, sorry, 4x minus 9. Okay, so what is this limit? This is pretty easy to calculate. You just plug in the x equals 4 into this, and you get 16 minus 9. So this limit is really, really easy to calculate. 16 minus 9, that limit is 7. Now let's take a look at the limit as x goes to 4 of the bigger function, x squared minus 4x plus 7. X squared minus 4x plus 7. Okay, so this is no problem. We can just evaluate this limit by plugging in 4. So this becomes 16 minus 16 plus 7. So this also equals 7. So we have this thing, the bottom, going to 7 as x goes to 4. And we have this thing going to 7 as x goes to 4. So that must mean, by the squeeze theorem, the thing that we're actually after, the limit as x goes to 4 of f of x, by squeeze theorem, the limit as x goes to 4 of f of x must be squeezed between these two limits, 7 and 7. So therefore, this limit also must be 7. So the only other thing to kind of keep in mind about this question is this little weird thing up here where they say, well, f of x is smaller than or equal to x squared minus 4x plus 7 when x is greater than or equal to 0. So why would they bother saying this? It might be possible then when x is smaller than 0, like when x is negative, that maybe this sort of situation doesn't hold. So should that concern us when we're doing the squeeze theorem? Not really, because we're looking for when the limit as x goes to 4. So certainly when we're close to 4, like 3.5 or 4.5 or in that neighborhood, when we're actually looking in the neighborhood of where we're taking this limit, this is true. Because in that neighborhood where x is close to 4, x is certainly greater than or equal to 0, which means that this is certainly true in the area that we're kind of interested in. So we're totally fine to use the squeeze theorem in this case. Okay. All right. So let's look at an example like this. A lot of times, if you're anything like me, when I was looking at this stuff the first time, absolute values always threw me off. So what we really need to remember for this entire course and probably for the rest of your life is that we really want to keep in mind that the absolute value function is actually two different functions. It's x minus 3 when x is greater than or equal to 3, and it's the negative of x minus 3 when x is smaller than 3. Okay, and the reason you split it up this way is what the absolute value does is whenever you have something like x minus 3 in absolute values, you take the positive version of this, you leave it alone as long as the thing inside the absolute values is positive. You just leave it alone. And when is the thing inside the absolute values positive? Well, it's positive whenever, or positive or equal to 0 whenever x is greater than or equal to 3. So whenever x is greater than or equal to 3, you don't even need these absolute values. They just go away. However, when the thing inside the absolute values is negative, so in situations where x is smaller than 3, what the absolute value tells you to do is take the negative of the version inside. So we take the negative of x minus 3 whenever we see absolute values. Okay? So we're going to need to be very careful about this because we have a limit as x goes to 3. So from the left and from the right, these types of limits are going to be a little bit different. So let's go back to the notes to kind of see what we should do about one-sided limits. All right, so the idea of a one-sided limit is instead of, you can take the limit as x goes to a number as x goes to a from the left. So for example, the limit of x goes to a from the left, this negative sign means that you should be thinking about what is happening to the function as x gets closer and closer to a, but only for numbers smaller than a. So if a was, say, 2, you'd be interested when x is going to a, like what is happening when x is 1.9, x is 1.99, when x is 1.99999. So what is happening as x gets closer and closer to a, but the numbers that you're using are always smaller than a. If that equals a limit L, we say that the limit as x goes to a from the left-hand limit is L. Right-hand limit works the exact same way. So now we're interested in what happens as you get closer and closer to x from numbers that are bigger than a. Like if a was 2, we'd be interested in using numbers like 2.001, 2.0000001, 2.000000000000001. So we're looking at what happens as x is closer to a from the right. If that is equal to L, then we say that the limit as x goes to a from the right of our function is equal to L. So what's the big deal between left-hand limits and right-hand limits? Well, if and only if these two limits, when you take the limit from the left is equal to L and the limit from the right is equal to L, then you can properly say that this limit as x goes to a is actually equal to L. If either of these things if these things do not end up being the same number, if the limit from the left is some number and the limit from the right is some different number, then this is not true. Then the limit does not exist. Okay, so this is the difference between left-hand limits and right-hand limits, and what they mean for what a limit actually is. So we're going to need that for this situation here, because notice that because the square or the absolute value of x minus 3, this function changes when x goes to 3. We're going to have to be really careful, because this function 2x plus the absolute value of x minus 3 is going to be different on one side of 3 than it is on the other side of 3. So we have to be very careful here and take the limit as x goes to 3 from the left and the limit as x goes to 3 from the right and see what actually ends up happening. So let's go ahead and do that. So let's first take the limit as x goes to 3 from the left. So we're interested in numbers like 2.0, 2.5, 2.7. So we're letting x get closer and closer to 3 from the left. And so when x is smaller than 3, what version of our absolute value should we be looking at? When x is smaller than 3, the version of the absolute value we should be looking at is the negative of this. And we can actually rewrite this if it's easier. We could rewrite this as 3 minus x if we really want to do that, which we do. So for us, the limit as x goes to 3 from the left of 2x plus the absolute value of x minus 3 is precisely equal to the limit as x goes to 3 from the left of 2x, and now we use the negative version of our absolute value because x is less than 3. So we use the negative version, so this becomes 2x plus, what is the negative version of this? 3 minus x. Okay, so at the end of the day, this becomes a limit as x goes to 3 from the left of 2x plus 3 minus x, which is just x plus 3. And what we see here is this limit is equal to 6, because as x gets closer and closer to 3, this gets closer and closer to 3, so the limit gets closer and closer to 6. Now let's see what happens as we take the limit as x goes to 3 from the right. So this is our function. This is the actual function that we're after. Oops, let's do this. 2x plus the absolute value of x minus 3. This is the function that we're actually interested in. This limit is equal to the limit as x goes to 3 from the right, 2x. Now what version of the absolute value are we going to use? Well, because we're interested in x values that are bigger than 3, we look up here and our absolute value function says whenever x is bigger than or equal to 3, we should be using this version. We should be using the x minus 3 version. So let's just stick that in. So plus x minus 3. And now we can go ahead and do this. 2x plus x is 3x. So this becomes limit as x goes to 3 from the right of 3x minus 3. And so as x goes to 3, 3x goes to 9, minus 3, this equals 6. So you can see here that the limit as x goes to 3 from the left is 6. And the limit as x goes to 3 from the right is also 6. So now we can fundamentally conclude that the limit as x goes to 3 of 2x plus x minus 3 is definitively equal to 6, because the limit from the left was equal to the limit from the right. Okay? So that's the idea behind one-sided limits. And so let's look at one of these examples. I think I might have mentioned this before. What we're going to use here is we're going to use these things. So these are good things to memorize. They showed up in a proof of some trigonometric derivatives, but these are good to just have in your back pocket in general, specifically for situations like this. So take a look at this limit. One might be inclined now. The limit is x, or theta goes to 0 of sine theta is 0. And the bottom also seems to be going to 0, so one might be inclined to use L'Hopital's rule. That might work just fine, but in some cases it might not. So you do want to have these trigonometric limits in your back pocket just in case you need to use them, and we actually will use them here because sometimes L'Hopital's rule does get you into trouble. So let's take a look at this. The limit as theta goes to 0 of sine theta. Oops. So, oops. Let's get rid of that. Start all over again. The limit as theta goes to 0 of sine theta over theta plus tan theta. And it's not going to let me do this. Tan theta. Okay. Tan theta is equal to, now what we can do is we can actually separate this, and this might not seem obvious to you, but we're going to use the trigonometric limits that we just took a look at to actually help us here. So we're going to try to get some sine theta over thetas out of this. So the limit as theta goes to 0 of, we're going to divide the top and the bottom by theta. So this is sine theta over theta. Okay, so I just divided the top by theta, and I'm going to divide the bottom by theta, so this becomes 1 plus tan theta over theta. Okay, so how does that really help us? Well, it hasn't really helped us too much. Actually, it looks like it made our lives more difficult, but in fact they haven't. So this looks like I should fix this. This is theta going to 0. So we're just going to leave this as sine theta over theta. So that's on the top. On the bottom, what do we have? We have 1 plus sine theta over theta, because that's the top part of tan. The top part of tan is sine theta times 1 over cos theta. Okay, so now look. This is where we're going to use those trigonometric limits. So as theta goes to 0 of the top, this is going to 1 by that limit that I just showed you. So this is going to 1. Let's see what's happening at the bottom. As theta goes to 0, this is also going to 1, and this is going to 1 as well. So whenever we have a limit of a product, we've seen these in the limit laws, these two things are each going to a number, so I'm totally okay to take the limits individually. So I can take this limit, it's 1, and I can take this limit, it's also 1, and I can just multiply them together. So this ends up being the limit as theta goes to 0 of sine theta over theta divided by 1 plus the limit as theta goes to 0 of sine theta over theta times the limit as theta goes to 0 of 1 over cos theta. Okay, so this is totally cool. I can break this up into two different limits because both of these limits exist. So by the law, I can do this. Also, because the top is going to a number and the bottom is now going to a number, I'm okay to split this up into a limit of the top divided by the limit of the bottom. This is all following from our limit rules, but being very careful before doing it. So the limit of the top as sine theta goes to theta by our trigonometric rule is 1. This is 1 plus the limit as sine theta over theta as theta goes to 0. This is from our trigonometric rule. This is also 1. And this, the limit as theta goes to 0 of 1 over cos theta is just 1, because when you plug in theta equals 0 into cos theta, you just get 1. So this is 1 over that. So at the end of the day, we get 1 over 2. So just a little use of our trigonometric limit laws. So we want to make sure we're kind of practice at using those if we need to. Again, you might have been able to use L'Hopital's rule, but sometimes, especially when you have sines and cosines, using L'Hopital's rule will just get you a lot of repetitive sines and cosines. So you do want to have this kind of in your back pocket. Okay, so here's a different kind of question when it comes to limits. So is there a number a such that this limit exists? If so, find a and find the value of the limit. So if you take a look at what happens as x goes to -2, so the limit as x goes to -2 of the bottom, so this is just x squared plus x minus 2. If you actually look at this limit, what is this limit? Plug in -2, you get 4 minus 2 minus 2, so that equals 0. So the limit of as x goes to -2 of the bottom, you're coming out with 0. So the only way that this limit can exist, the only way it can be anything other than infinity, is if the top also goes to 0. So we need to ensure that the limit as x goes to -2 of the top, 3x squared plus ax plus a plus 3, we want to make sure that that is also 0. And the reason we want to do that is because if it was any other number, if it was 4, or if it was -6 or something, then what we would have a situation where the top is going to a number, but the bottom is going to 0, in which case that would go to positive or negative infinity. We would like this limit to be some sort of finite limit, so we're going to ensure that the top is also going to 0, so there's some sort of competition between the top and the bottom. So let's make sure that that happens. So the limit as x goes to -2 of 3x squared plus ax plus a plus 3. Well, this is no problem. We can just plug in x equals -2 into all of this. So we get 3. This ends up being 4. -2 squared is just 4. Which is 4. As x goes to -2, ax goes to -2a plus a plus 3. So when I add that all up, I get 12 plus 3 minus a. So we get 15 minus a. So we want 15 minus a to equal 0. Because what that will ensure is that this limit, this top, is actually going to 0 as well. So what choice of a actually does this? A equals 15. So if we make a equal to 15, then we're guaranteed that this limit of the top part is also going to 0 at the same time that the bottom is going to 0. So perhaps this actually might survive. So now that we have that a equals 15, let's go ahead and calculate this limit and see what happens. So the limit as x goes to -2. So now that we know that a is 15, we have 3x squared plus 15x plus 18 divided by x. I'm going to go ahead and factor this. This factors into x minus 1 and x plus 2. And I think you can understand why I want to factor that already. And that's because we're going to do some factoring and some canceling. Okay, so this ends up being equal to, so two numbers that multiply to be 48 and add to be 15. This ends up being, let me see here, two numbers that add, multiply to be 48 and add to be 15 are 18 and 3. Nope, not quite. Let me think. Oh, well, let's just take out a 3. That's probably going to make our lives easier. Let's just take out a 3 first before doing all that complicated process. Now that I see that 3 can be pulled out of both. So this is limited as, I'll take 3 out of everything, so this becomes x squared plus 5x plus 6. That's way easier to work with, divided by x minus 1, x plus 2. So now we can factor the top quite easily. We have 3. Two numbers that do this are x plus 2 and x plus 3. So we have x plus 2, x plus 3. And we divide that by x minus 1 times x plus 2. So now these x plus 2's cancel that one and that one, which makes our job much easier. So now the limit as x goes to 2, this is the limit as x goes to negative 2 of 3x plus 3 divided by x minus 1. And when we plug that in, we get 3 times 1 divided by negative 3. And so this ends up being negative 1. Okay? So again, the whole point of this one was we have this complicated expression up here, and we want to make sure that this limit actually goes to a number. So we have to figure out an a that does that. As x goes to negative 2, the bottom goes to 0. So we want to make sure we pick an a that also makes the top go to 0. So we calculated that limit. When we calculated that limit, we found that it was 15 minus a. We want to make sure that that was 0. So that meant a equals 15. And because a equals 15, now we could go back in and actually calculate this limit properly using our factor method that we talked about a couple slides ago. Okay, so this is the next question. So let's talk about this. So it's one-handed limits. So let's talk about vertical asymptotes. The idea of a vertical asymptote is whenever you take the limit as x goes to a from the left, so if the limit from x goes to a from the left, from the right, or from both sides is equal to infinity or negative infinity, whenever this happens, you're going to encounter a vertical asymptote. So this only has to happen on one side or the other of a, or it could happen on both sides of a. They could both be different. Whenever you have anything that happens where x goes to a, and then the function goes to, the limit goes to infinity or negative infinity, this is when we have something called a vertical asymptote. Horizontal asymptotes. If you have a situation, so to calculate horizontal asymptotes, you've seen this before, I'm sure. You've done many, many questions like this. The idea is if we take the limit as x goes to infinity of our function, there should be f of x in here, so there's a typo. So the limit is as x goes to infinity of f of x, if that ends up being a number, like 7, then that means that there's a horizontal asymptote at 7, at y equals 7. For example, if you take the limit as x goes to infinity of 1 over x, that limit equals 0. So we could then say there's a horizontal asymptote at y equals 0. Okay, before we get to continuity, let's do a couple questions like that. So let's take a look at this, this question here. So let's see what happens. As the limit as x goes to 1 of the top, 2 minus x, that is, no problem, just plug in a 1, that equals 1. The limit as x goes to 1 of the bottom, x minus 1 squared, is equal to 0. So we have a situation here where the top is going to 1 and the bottom is going to 0. So we have a little bit of a problem. Unfortunately, we're not going to be able to do anything like canceling or any conjugate stuff like we've been doing so far. This, we're kind of just stuck with the situation that the top is going to a number and the bottom is going to 0, which means this function is going to infinity or negative infinity. So which is it? Is this limit infinity or negative infinity? Well, the top is going to 1, so the top is going to 1, and the bottom is going to 0, but notice that the bottom is always positive. Okay? And the top is always going to 1. The top is always positive as well. So because the top is positive and the bottom is positive, this limit as x goes to 1 from both sides, as x goes to 1 from the left and as x goes to 1 from the right, of 2 minus x, x minus 1 squared is equal to positive infinity, no matter which way you take it from. If this, if the bottom was, say, just x minus 1, so not x minus 1 squared, then the number on the bottom would still be going to 0, but if you took the limit as x goes to 1 from the left, it would be, as x goes to 1 from the left, it would be a positive number, a negative number, which would mean this would be negative infinity. As x would go to 1 from the right, it would be a positive number, so from the right, this would be positive infinity. So if the bottom here was just x minus 1, not x minus 1 squared, you would have different behaviors on each side of 1. So you would still have an asymptote. This certainly means that there's an asymptote, but you would know that the behavior from the left side of the asymptote is different from the right side of the asymptote. One would be going to positive infinity, one would be going to negative infinity. So let's look at some horizontal asymptotes. So here's kind of a tricky question. Usually when we're talking about asymptotes, and we'll see maybe a question like this a little bit later on, what we want to do is we want to take the limit as x goes to infinity, and usually there's a nice way of like canceling out the highest power of x, or from the top and the bottom, and it makes our life easier. Unfortunately here, we don't have a top and the bottom to cancel the largest power of x. So what are we going to do? Well, yes, okay, everyone loves L'Hopital's rule, so you could use L'Hopital's rule if you want. Maybe that'll get you some answers. But we're not going to use L'Hopital's rule. We're going to have lots of questions like that later on. So let's just do this the old-fashioned way. And what we need to get is we need to get a top and a bottom out of this. And then we can use our divide by the highest power of x trick. So to get a top and a bottom, we're going to multiply by the conjugate again. So let's see what this looks like. Limit as x goes to infinity of square root of 9x squared plus x minus 3x times the conjugate is 9x squared plus x plus 3x, because that's the opposite sign. And of course we don't want to change the question, so we have to multiply the top and the bottom of this question by the conjugate. So we're going to multiply it like this. Okay, well, that looks like it's more confusing, but at the end of the day, it's actually going to help us. So when we actually remind ourselves that this is over 1, so when you multiply the top, you get 9x squared plus x minus 3x squared. So the square root goes away. The middle terms cancel when you FOIL this out, and then the final thing is minus 3x times plus 3x is minus 3x squared, and the bottom is just going to stay the conjugate. 9x squared plus x plus 3x. Okay, so let's see if we can simplify the top a little bit. Limit as x goes to infinity of the top is just going to actually simplify. This minus 3x squared is going to be negative 9x squared. So the negative 9x squared cancels out with the 9x squared. So this actually cancels out with this. So it simplifies our life, and all we're left with at the top is x. So now we have still on the bottom this 9x squared. Let's just delete that. We have the square root of 9x squared plus x plus 3x. And now that we have a top and the bottom, now we can actually go ahead and use our largest power of x trick. So what is the largest power of x here? Well, it kind of looks like there's an x squared here. So we might be inclined to think that the largest power of x is 2, because there it is, x squared. But we have to remember that that's inside of a square root. So actually this behaves more like the square root of this stuff. And the square root of this stuff acts more like x rather than x squared. So the actual largest power of x in this example is x to the power of 1. So we're going to multiply the top and the bottom by 1 over x. And as x goes to infinity of 1 over x. Oops. Let's see if I can clean that up. 1 over x times x over, and we're going to multiply the bottom by 1 over x as well. Square root of 9x squared plus x plus 3x. All right. So when we do this, the top goes to 1, right? 1 over x times x is just 1. And then if we multiply the 1 over x into the square root, first of all, let's keep in mind that because we're going to positive infinity, these numbers, these x values are really, really big, and they're positive. So when I multiply the 1 over x inside the square root, I don't have to leave a minus sign out here, right? This is actually just a positive number, positive square root. This goes in here, and we're all set. So we can actually just multiply that 1 over x in without worrying about any signs. So the 1 over x goes inside, and you have the square root of 9x squared over, now when 1 over x goes inside the square root, of course we have to square it, so this becomes 1 over x squared plus x over x squared, and this 1 over x, when we multiply by here, becomes plus 3, so that's okay. And now when we calculate all of this, this ends up being the limit as x goes to infinity of 1 over the square root of 9 plus 1 over x plus 3. Now, as x goes to infinity, this 1 over x goes to 0. Right, because the limit as x goes to infinity of 1 over x is 0. So this actually makes it 1 over the square root of 9 plus 3, which is 1 over 3 plus 3, which is 1 over 6 is the limit. Okay, so here's an example where we had this something that doesn't look like we can divide by the top and the bottom, divide the top and bottom by the largest power of x, but we can make it into 1 by multiplying the conjugate. And the reason we chose to multiply by the conjugate is because we have this square root here, and whenever we multiply the conjugate, it makes the square root kind of go away on the top, which is kind of nice. Okay, so how about this? This question, limit as t goes to infinity, looks like it might be a conjugate question, and you're more than welcome to try that out. That might be a good idea, but in fact it's actually much easier. In fact, we can jump, because we have a kind of a top and a bottom here, we can actually just jump straight to multiplying dividing the top and the bottom by the largest power of t. In this case, the largest power of t is t squared. So the limit as t goes to infinity of, I'm going to rewrite this as t to the 1/2 plus t squared over 2t minus t squared. So I'm going to multiply the top and the bottom by 1 over t squared. 1 over t squared. And that's equal to the limit as t goes to infinity of, this ends up being, when you multiply 1 over t squared into this ends up being t to the negative 3/2 plus 1 over, this becomes 2 over t, and then this becomes minus 1. And as t goes to infinity, this goes to 0, this goes to 0. So at the end of the day, I'm just left with plus 1 over minus 1. So this limit is negative 1. So this is a situation where you might be inclined to try this conjugate method, and it might be okay. That might work totally fine. But since we already had a top and the bottom, I just divided by the largest power of t for the top and the bottom. And then I was able to take that limit. Okay, so in this case, because the limit as t goes to infinity, we would say that there is a horizontal asymptote at negative 1. Up here, we would also say that there is a horizontal asymptote at 1/6. Okay, because those limits as t went to infinity was equal to a finite number. Okay, so let's try an even trickier example. Let's see if we knew that we had a function, f of x, that actually behaved in this way. Could we take the limit as x goes to infinity of this? Now, your squeeze theorem alarm bells should be going off, because this looks like f of x is being squeezed in between two things, and it is. So we are going to use the squeeze theorem. However, it's not really clear how to do this, because we have 4x minus 1 over x. So the limit as x goes to infinity of the top is infinity, the bottom is infinity. Same with on the right hand side, infinity over infinity. You might be inclined to use L'Hopital's rule, but again here we can actually avoid L'Hopital's rule by just realizing this actually simplifies. So for example, the limit as x goes to infinity of the smaller function, 4x minus 1 over x. Again, lots of people out there would be inclined to use L'Hopital's rule. You can just actually look at this, divide both of these terms by x. Limit as x goes to infinity of 4 minus 1 over x. And as x goes to infinity, this goes to 0, so this limit is actually just 4. No L'Hopital needed. The limit as x goes to infinity of the bigger function, 4x squared plus 3x over x squared. This is equal to, again, we can divide the top and the bottom by the largest power of x. This becomes limit as x goes to infinity of 4 plus 3 over x divided by 1. This is also 4, because this goes to 0. So this thing, the bigger function, is going to 4 as x goes to infinity. The bottom function, or the smaller function, is also going to 4 as x goes to infinity. And the function that we're interested in, this f of x, is always in between the two. So by the squeeze theorem, we can say that the limit as x goes to infinity of our function f of x, which is what we're interested in, this is actually equal to 4 because the function that's bigger than it is going to 4. The function that's smaller than it is going to 4. The function that's bigger than it is also going to 4. So our function is squeezed in between the two. It also has to go to 4. So here we would also say that there's a horizontal asymptote at y equals 4 of our function. I don't even know what it looks like, but as long as this is true, I can actually calculate the horizontal asymptote as x goes to infinity. Okay, so I know that on previous tests and previous exams, you've seen a lot of true and false questions, and this is where a lot of people actually get tripped up. So let's do a couple true and false questions. I should point out that if you want to see a bunch of true and false questions that really test your knowledge, I encourage you to check out the textbook, the Stewart Calculus textbook, any of the versions. There's a new version that's over $100, but you might not want that. So there might be old copies of Stewart in the library or old copies of Stewart floating around online. Try to find Stewart Calculus and look at all the true and false questions that happen at the end of the chapters. Those are really good ones to test your knowledge of these types of theorems and all that kind of stuff. So we're going to do some true and false questions here. So let's just take a look at this. If x is any real number, I know there's a lot of people, probably myself included, when I was doing this for the first time, that might be inclined, whenever you take the square root of x squared, you always get x. So this is true or false? This is false. And I think you can understand the reason. So let's just say we had x equals -3. Okay, if x equals -3, then the square root of -3 squared is equal to the square root of 9. That equals 3. So does the square root of x squared, in this case, equal x? Absolutely not. These two numbers are different. So this is certainly an example where you can see that this is not true. Okay, so be careful about this. When you take the square root, there's always a positive and a negative version. Okay, how about this one? True or false? You have this limit as x goes to 4 of these two pieces equals the two pieces separately. So what about this? This is a situation where one would be inclined to use the limit laws. And the limit laws certainly say that we can separate things. But remember what I said about the limit laws before. You can only separate things when these two limits exist. So the limit as x goes to 4 of 2x over x minus 4, it does not exist. This is infinity. All right, because as x goes to 4, the top goes to 8, the bottom goes to 0. This goes to infinity. The limit as x goes to 4, this goes to infinity. Well, I guess depending on what side you're coming from. But anyway, this limit does not exist. This is not a number, so you just can't separate them. However, so let me actually just delete this. However, what I do want to point out is, so this is false because, like I said, the limit laws say that you can only separate these two things if each of these limits exist, if they're actually a number. Then you can separate them and do them independently. If you actually look at this, in theory, this would look like this is something to do with infinity minus infinity, maybe do some L'Hopital's, like I don't know, but you can't even separate them. If you leave them together, then we can actually calculate this. The limit as x goes to 4 of 2x over x minus 4 minus 8 over x minus 4. If you leave them together and you do this as one big function, this is actually 2x minus 8. The limit as x goes to 4 of 2x minus 8 over x minus 4, which is, and now we can go right ahead and use our factoring. So this is 2x minus 4 over x minus 4. So the x minus 4's cancel, and you just get 2. So this limit on the left-hand side is 2. But the limit on the right-hand side is a whole bunch of garbage because none of these limits exist or they're infinite. So this is a little thing where you really have to be careful. I mean, you like to use your limit laws, you like to separate things, and you're quite good at it. But the problem is you can only do these things under the conditions that they're allowed. And the condition that is allowed to say that you can actually separate these two limits is if these two limits are actually going to a number. Here's an example where if you keep things together, you get a limit, and if you split them apart, you don't. So in this case, you're not allowed to split these up. You have to keep them together. And the reason is because when you do split them up, the things you split them up into, these limits are infinite or they don't exist. So you can't do it. You need to keep them together. All right, so here's another one. True or false? If I have a limit as x goes to a of f of x, so I have some function as x goes to a, that limit exists. But as x goes to a, g of x does not exist. So when I go, or is infinite, if you want to think about it that way. So you have some limit that doesn't exist when you take x going to a of g of x, but as x goes to a of f of x, this does exist, g of x doesn't exist. Then the limit as x goes to a of f of x plus g of x does not exist. So is this true or false? So this is actually true. And let's see if we can prove it. So assume assume the converse. Assume that this is not true. Assume that this is false. So assume that the limit, oops, let's delete this. The limit as x goes to a of f of x plus g of x together, so we're going to keep them together, exists. So this is the opposite, right? We're saying it's true that it does not exist. So to prove it, we're going to assume the opposite and see if we run into problems. So assume that this actually exists. Well, then I don't think it is really too hard to see that g of x is actually equal to f of x plus g of x minus f of x. Nothing really tricky there. I just rewrote g of x in some sort of confusing, convoluted way. Well, if we actually then do this, I take the limit as x goes to a of g of x is equal to the limit as x goes to a of f of x plus g of x, in brackets, minus the limit as x goes to a of f of x. Now, why can we do this? Why can we do this on the right-hand side? Why can we separate this into this limit minus this limit? The reason we can do this is because we've assumed that this exists. So this is a totally fine number. And we already know the limit as x goes to a of f of x is a totally fine number. So our limit laws say as long as after we separate them, these separate things go to a number, they're actually a number, I'm allowed to separate them. So I did. So here's my separated version. This exists by assumption. So this exists. This is a number. This exists. This is some number. But look at the left-hand side. The limit as x goes to a of g of x says it does not exist. This does not exist. This does not exist. So now we have a problem. The thing on the left-hand side doesn't exist. The thing on the right-hand side is just a subtraction of two things that exist, like 5 minus 2 or something. So we have a problem here. So what was the problem? The problem, so this is a contradiction. There's a problem here. And the problem is that we assume that this thing existed. Right? Way up here we assumed it existed. So we can therefore say that our assumption must be wrong. And what does that mean? That the limit, that must mean that the limit as x goes to a of f of x plus g of x, when taken together, does not exist. Which is precisely what we said, that this statement is true. Okay, so the first time you might see that proof, that might make you a little bit squeamish and you might not like it and you might not understand it. That's okay. These things are tricky. But what I really want to point out about these types of questions is these are the types of questions that really get at whether or not you understand the theorems and whether or not you understand the rules that you like to apply. Like the squeeze theorem. Do you really understand the squeeze theorem? Sure, you can apply it, but what situations can you apply the squeeze theorem? What situations can't? What situations can you use the limit laws? Which situations you can't? These are the types of questions that really dig at whether or not you understand what's going on. So I really encourage you to look at as many of these as you can, kind of after you've done your main body of studying, which is, you know, how to calculate things, how to do things. So these are really good questions. So let's take a look at another one. True or false? The limit as x goes to 6 of f of x times g of x exists. So this thing is okay. So that must mean that the limit must be f at 6 times g at 6. So is this true or false? This is actually false. So what this is actually saying that if this limit exists, the limit as x goes to 6, of the two things multiplied together, if that is okay, then you're allowed to do you're allowed to calculate the limits separately and actually figure them out separately and then multiply them together. This looks like a limit law, but is exactly the reverse of a limit law. The limit law says that you're allowed to do this as long as these numbers exist. You can separate them as long as these numbers exist. There is no guarantee in this question that these numbers actually exist. So there's no guarantee that you can do this. And let me give you a counterexample. Let's take a look at this. The limit as x goes to 6 of x minus 6 times 1 over x minus 6. Okay, so here's f. This is a g. Okay, well, this is kind of easy. As long as we keep them together, x minus 6 times 1 over x minus 6, this is just 1. So this limit is 1 as long as we keep them together. However, this is saying that I could do this. Of x minus 6 times 1 over x minus 6. The thing that they're actually saying is that I could do this. F at 6 times g at 6. So this is okay. I can do that. This is very, very bad because I can't just plug in x equals 6 into g of 6. So I can't do this. This thing is very, very bad. So what this is saying is, sure, this limit exists. There it is. But I can't separate them. They have to stay together in order for this limit to make sense. By separating them, I actually run into a problem. So even though the limit as x goes to 6 of the functions stuck together exists, that does not mean that I can just plug in the numbers separately. So here's an example again where you really have to keep track of what the limit rules are saying. Okay, so that's a lot of stuff about limits. So let's take a look at continuity, and then maybe we'll take a little bit of a break so people can go to the washroom or grab a drink. Maybe a 5-minute break after we talk about continuity. So let's talk about continuity. Here is a continuous function. Everyone knows from high school what a continuous function is. A continuous function is just a function where you can draw it without lifting your pen, right? So here, no problem, I can draw this nice function. If I had any skills at all, I could just draw that function without moving my pen. No big deal, that's continuous. This is a discontinuous function. So here we have something that has a hole in it. Here we have a jump discontinuity, so we have something that goes from here to here, so it jumps up. Here we have a function where there's a hole in it and the actual value of the function is way up here. Okay, so this is an example of a function that's actually discontinuous in 3 places. This one, and this one. At x equals 1, x equals 3, and x equals 5. So mathematically, what do we mean by a discontinuous function, or what do we mean by continuity? So this is it. This is what it means to be continuous. This is the whole definition of continuity. A function is continuous at a point A, so it only makes sense to talk about the continuity of a function at a specific point if the limit as x goes to A of the function is equal to the value of the function at that point. Okay, so think about that for a second. That means 3 things actually have to be true. First of all, the left-hand side has to be true. Actually, let's look at the right-hand side. So the first thing is this has to be true. So you have to be able to actually plug in A into your function. If you can't do that, if, for example, A is not in the domain of f, if you're not allowed to plug in A into your function, then this thing on the right-hand side doesn't even exist. This is some sort of unicorn, some sort of monster that doesn't exist. Okay, so you can't, if A is not in the domain of f, this right-hand side doesn't make any sense. So certainly, if something needs to be continuous, f has to be defined at A. The limit as x goes to A of f of x has to exist and is not infinite. So the left-hand side, look at the left-hand side, this says that the limit as x goes to A of f of x. They're saying this needs to be a number, which means that the limit from the left has to equal the limit from the right, because that means that the limit exists. And it has to be a finite number. Okay, so the limit on the left this thing has to be a finite number. That's the second thing that has to be true. And finally, the third thing has to be true is these two numbers have to be the same. This number on the left has to be this number on the right. So there are three things that you need to check to make sure a function is continuous. First of all, that you're allowed to plug in the value at a. Second of all, that you're allowed to, the limit as x goes to a from the left and the right is the same number. And that these two numbers, the left-hand side and the right-hand side, actually are the same number. So let me show you how that breaks down. So here is a situation where f at 1 does not exist. Okay, you're not allowed to plug 1 into your function. So here's a situation where it's discontinuous because f of 1 does not exist. 1 is not in the domain of this function. So there's certainly a discontinuity here. Here, what you have is the limit as x goes to 3 from the left is this thing, and the limit as x goes to 3 from the right is this thing. So these two limits are different. This means that there's a jump discontinuity. So there's a discontinuity here. What's happening to the function as you get closer and closer to 3 from the left is different than what's happening to the function as you get closer and closer to 3 from the right. So this is a situation where it's discontinuous. And finally, here's a situation where the limit as x goes to 5 from the right, that's going to a number. The limit as x goes to 5 from the right is also going to a number. In fact, they're going to the same number, so everything should be cool here, except the value of the function at that number is way up here. So here's the third type of situation, that these numbers are not true. Even though the limit exists, it's this, and the function exists, it's this. If these two numbers aren't the same, then you have a discontinuous function. So this is the third thing that you need to check. And just some sort of technical points about continuity. We can talk about whether or not a function is continuous from the left. If it's true that the limit as x goes to a from the left of the function is equal to the function at a. So this is not even worrying about what's happening from the right. This is the opposite. So if you're only interested in what's happening as x goes to a from the right of the function, if that matches the value of the function at a, then it's continuous from the right. So for example, up here, this is continuous at 3 from the left. The limit as x goes to 3 from the left is equal to the value of the function at 3. So this is continuous from the left, but it's not continuous from the right at 3. Because the limit as x goes to 3 from the right is up here, the value of the function is down here. It is not continuous at 3 from the right, but it is continuous at 3 from the left. But in general, it's not continuous at 3. Only continuous at 3 from the left. And continuity on an interval, it's if we know that a function is continuous everywhere on an interval, if it's continuous at every point, so every point between, say, -2 and -1 or something, or -7 and 15, if we know that it's continuous at all of the points in there, then we say that it's continuous on that interval. Okay, so just here's some definitions. We can say that f of x is continuous on the interval ab if it's continuous for all of the points inside of ab. So it's continuous at all c values inside of a and b. It's continuous on the closed interval ab if it's continuous at all the points in that interval and continuous at the right, on the right of a and on the left of b. Okay, so as you get closer and closer to b from the left, it's continuous. As you get closer and closer to a from the right, it's continuous. Then we can say that it's continuous on the closed interval. However, if this isn't true, then we say that it's continuous on the closed interval a comma b. So notice that b is not included here because it's not continuous from the left at b. On the other hand, if we know that this isn't true, then we have to exclude the point a on our interval. So we know that it's continuous on this interval, but a is not included because this is not happening. Okay, so just some technical points about continuity on an interval. So some continuity theorems. Suppose that you know, these are the ones that you're really going to use a lot whenever you're talking about continuity. If you know that f and g are continuous at a point, right? So say you know that sine x is continuous at 0, and cos x is also continuous at 0, and c is any number, then the following things are true. If you add the two functions together, that's also continuous at a. If you subtract the two functions, that's also continuous at a. If you take that constant and you multiply it to f, that's also continuous at A. If you multiply the two functions together, sine x times cos x, that's also continuous at A. If you divide the functions, that's also continuous at A, provided the bottom function at A is not 0, because you don't want to run into that situation. So for example, let me just give you a really, really quick example. Say I know that f is equal to cos x, and g is equal to sine x. This is continuous at 0. You can go ahead and check by the definition. This is also continuous at 0. You can check by the definition. What that would mean is sine x plus cos x is continuous at 0. Cos x minus sine x, that function is continuous at 0. Any number times cos x, like 7 cos x, that's continuous at 0. Sine x times cos x, that's continuous at 0. And actually we have a situation here where this is false, right? Because cos x is continuous at 0, no problem. Sine x is continuous at 0, no problem. But sine of 0 is 0. So this is actually a situation where this would not be true. So cos x divided by sine x is not continuous at 0, because sine x, the bottom part, is 0 when x equals 0. Actually, I'm going to keep that in. So just some examples of things that you know. So rather than prove all this stuff, you just need to be able to state this. Say you're doing a question. Any polynomial is continuous everywhere. So anything that looks like, x to the 4th minus 3x squared minus 8, this is continuous everywhere. So any x that you can imagine, this is a continuous function, no big deal. Other things, rational functions. So whenever you have a polynomial divided by a polynomial, this is continuous. Any square roots or roots are continuous. Trigonometric functions are continuous. These are continuous at every single x location known to man, as long as those are in their domain. So for example, a rational function, if the function is 0 in the denominator, it's not continuous there. So these functions are continuous. All the functions that you know and love are continuous everywhere on their domains. Finally, if I put a function inside of another function, so say I have this function g of x, and I have a function f of x, and I know that g of x is continuous at a point A, and f of x is continuous at g of A, then f at g of x is continuous at A. So for example, say I had, say g is equal to e to the power of x, and f is equal to cos x, for example. G is continuous, and let's just say a is equal to 2. So g of x, which is just the exponential function, is continuous at 2. No big deal. You can plug into the limit from the left, so the limit from the right is equal to e at 2. No problem. So g of x is continuous at a equals 2, and cos x is continuous at e to the power of a. So when I plugged in a into g, so this is g of a, when I plug that in, f is continuous there. So f is continuous at this number. Then that must mean that f of g of x, which is this, is continuous at 2. Okay, so that just means you're allowed to kind of plug in a function inside of a function, and at that point a, everything works fine. This new kind of hybrid function that you've made by plugging in e to the power of x into cos x, this is also continuous at that point. Okay, and that gives us a new limit law. If we know that f is continuous at b, so f is continuous at b, and the limit as x goes to a of g of x is equal to b, then when I do the limit as x goes to a of f of g of x, then I can just pull the limit inside the function f. I can just move the limit inside here, provided that f is continuous here. This is b, right? Limit as x goes to a of g of x is b. This is b. So as long as x is continuous there at that point, then I'm allowed to pull this in. If this is not true, if f is not continuous here, I'm not allowed to pull this limit in. So for example, here's a situation where I can. The limit as x goes to 4 of sine e to the x. I can do this because after I do this, this is equal to e to the 4, and sine is a trig function. Sine is continuous everywhere. on its domain. So certainly sine is you have no problem plugging in e to the 4 into sine. So this is certainly true. So what you want to watch out for, and the problem that you want to run into, is situations like this. Suppose I had limit as x goes to 0 of, say, sine of 1 over x. Right? Is this equal to, can I pull the limit right in? Sine of limit as x goes to 0 of 1 over x. Can I do this? And the answer is no, because the limit as x goes to 0 is infinity. Sine, this is, first of all, it's crazy to actually do this, but sine is not continuous at this area. In fact, sine isn't even defined. So I can't pull it in this case. Essentially, this rule says you're allowed to pull things through. You're allowed to pull the limit inside the function. You're allowed to pull the limit inside the function as long as after you do it, everything works out okay. All right, so let's talk about some continuity examples. So, explain why the function is discontinuous at a equals 1. So here's a situation where they give us f of x, and they would like to know whether or not this function is continuous at a equals 1. All right, no big deal. Let's just check to make sure everything is fine. So the limit as x goes to 1 from the left of our function is equal to the limit as x goes to 1 from the left of, well, which version of this function should we be using? Well, when x doesn't equal 1, so for us, you know, we're taking x is 0.9, 0.99, 0.99999. So we're looking for x's that are not equal to 1. We must use this version of the function, x squared minus x over x squared minus 1. And I can actually factor this. This is the limit as x goes to 1 from the left of x minus 1 over x minus 1, x plus 1. Okay, so these x minus 1s cancel, and now I can just plug in the 1 in, and I get that when I plug in 1, I get 1 over 2, so this ends up being 1 over 2. Okay. Now, if I do the same thing from the right, the limit as x goes to 1 from the right of my function, f of x, is equal to the limit as x goes to 1 from the right of my function. Which version of my function should I use? Well, I'm looking at x's that are like 1.01, 1.0001. So I'm looking at x's that are not 1, because I'm taking the limit as x goes to 1. So I need to use the not 1 version of my function, which is this, x squared minus 1. So this is equal to the limit as x goes to 1 from the right of x, 1 minus x. So this is the exact same calculation we did up at the top there. X minus 1, x plus 1, and so when I cancel out these, oops, I think I might have this, it's not going to let me, this is going to be x. Let me see here. I'm going to have to redo this. Let me just delete this, and I'll try to do this again. Maybe not. Limit as x goes to 1 from the right. Now the top, when I take out an x, is going to give me x minus 1. So this cancels with this. And again, I'm left with that this limit is 1/2. So the limit as x goes to 1 certainly is 1/2. The limit as x goes to 1 of my function is equal to 1/2, because the limit as x goes to 1 from the left is 1/2. The limit as x goes to 1 from the right is 1/2. So certainly I'm justified in saying the limit as x goes to 1 of my function is actually 1/2. It's the same from both sides. However, the function at 1 is equal to, well, you go up here and it says whenever I have x equals 1, the value of my function is 1. So f at 1 is equal to 1. These things are not true. So therefore we conclude that f is discontinuous at x equals 1. Okay, because the limit from the left and the limit from the right, that was okay. That gave me a limit, which was 1/2. But the value of the function at 1 was actually equal to 1. So that's why it's discontinuous at x equals 1. Okay, so find the value of a constant c so that this function is continuous everywhere. So they want to make sure that there's no discontinuities in this function. All right, so by the definition, in theory, we should check to make sure that f is continuous at every single point ever. You know, every x value, we should make sure that the function is continuous. However, look at the way that these functions look. Whenever x is less than 2, this is what the function is. This is a polynomial. This one, also a polynomial. So as long as x does not equal 2, we have two polynomials. So when x does not equal 2, f of x is a polynomial. Therefore, we know f of x is continuous everywhere except possibly x equals 2. When x equals 5 or 10 or whatever, these are just polynomials. So certainly no problem. Our function is continuous there because these are polynomials. The only place that something weird can happen is if at x equals 2, when the functions change from one to the other. So what we need to make sure is we need to make sure that c is chosen. Need to choose c so that the limit as x goes to 2 is f of x equal to the function at 2. This will make sure it's continuous at 2, and we know it's continuous everywhere else, so then we know it's continuous everywhere. So let's just do that. The limit as x goes to 2 from the left of f of x is equal to, all right, limit as x goes to 2 from the left. Which version of the function should I be using? This one, c. Oops. The version x goes to is the limit as x goes to 2 from the left of c x squared plus 2x. And when I plug in x equals 2 into this, I get 4c plus 4. Okay. Now the limit as x goes to 2 from the right of my function is equal to the limit as x goes to 2 from the right of what version of the function should I be using? I should be using all the value or the version of the function where the x's are bigger than 2. So right here, x cubed minus cx. So when I plug in 2 into this, I get 8 minus 2c. So the limit from the left is 4c minus 4. The limit from the right is 8 minus 2c. So I need to make sure that these are the same. So let's just force them to be the same. 4c plus 4, we want 4c plus 4 to equal 8 minus 2c. And if I rearrange this, the 2c comes over here. I get 2c equals 4. So that must mean c equals 2. I feel like I've done that wrong. 1 second. Yeah, so you get 2c, and then, no, that should be right. Unless I've made a mistake somewhere else. 4c, so oh, sorry, this ends up being 6c. That's my mistake. So this, when you move the 2c over, it becomes 4c plus 2c, and this is got to equal 4, which means c has to equal 2/3. Okay, and so if we have c equals 2/3, then our let's just check that. So the limit as x goes to 2 is now equal to of our function. Limit as x goes to 2 of our function f of x is equal to, well, if we go back in and we plug in c equals 2/3 into these, we have into either one of them because they're now the same. We have 8 over sorry. We have 4 times 2/3 is plus 4 times 2/3 plus 4 is equal to 8/3 plus 12/3, which is 20/3. Now, what is the value of f at 2? Right, because it's great for us that we've made sure that this limit, the limit from the left is equal to the limit from the right. That's good for us. However, we need to make sure that that limit, which we just calculated, which is 20/3, we need to make sure that the last part about continuity is we need to make sure that that is actually equal to the value at 2. So let's plug in 2 into our function. What version of the function should we use when x equals 2? When x equals 2, we should use x cubed minus cx. So this should be 2 cubed minus c times x. So 2 cubed minus c times 2. That equals 8 minus 2c, which is 8 minus 2 times 2/3, which equals 20/3. So these two numbers are the same, which means we're in good shape. So this is the value for c that we need. So f of x, c equals 2/3, means f of x continuous everywhere on -infinity to infinity. And again, the reason is because we know it's continuous everywhere else. It's continuous when x is smaller than 2. We know that it's continuous when x is bigger than 2 because these two functions are polynomials. The only place we suspect that something might go wrong is at x equals 2. So now we choose c to make sure that the limit from the left at 2 is equal to the limit from the right at 2, which is equal to the function at 2. And we've done that. So this is the special c that makes it work. Okay. So what's the big deal about continuity? It leads to something called the intermediate value theorem. And the intermediate value theorem is essentially this. If you have some function that is continuous on an interval, so you can draw it without lifting your pen up or your pencil up, n is some number in between these two, then there has to be some number c such that the value at when you plug in c is equal to n. What that means is, I'll just draw you a little version here. So here is my axis. So here's A, here's B, here is, this is f at A, this is f at B, so this is f at B, if I can actually get it to work properly, f at B, and this is f at A. What the intermediate value theorem is, if there is some number n in between f at A and f at B, so any number that I want, so let's just call this n, I challenge you to draw a continuous function between A and B, so any continuous function, you can make it wavy, you can do whatever you want. I need you to connect these two dots without lifting your pen, without crossing this line. Try that. Try to figure out a way to connect A and B without going through this value n. And what the intermediate value theorem says, as long as it's a continuous function, there's no way to do this. You're going to go through, at some point, this point, and this point is what they call C. This is the point C. There has to be some point C where you cross this value n. This is what the intermediate value theorem says. As long as your function is continuous, this has to happen. Of course, if it's discontinuous and you just go down here and you jump up, right, you can cross this line. But if your function is continuous, there's no way to do this. This is what the intermediate value theorem says. And so who cares about the intermediate value theorem? Okay, that's cool, neat little math trick. But what it actually ends up doing is it allows us to say that there are some solutions to problems even if we don't calculate the solution. Our whole lives we've been trained to find the solution to an equation, but as you grow older and you get more and more complicated problems, you will find that you might not be able to find the solution, but maybe you just want to make sure it's there. So that's what the intermediate value theorem is good for, or one of the things that the intermediate value theorem is good for. So for example, use the intermediate value theorem to show that there is a root of x4 plus x cubed minus 3. What that means is show there is an x. I'm going to call it x star. So that, actually, I'm going to call it c. Show that there is a c, so that when I plug in c into my function, c to the fourth, this special number, plus c minus 3 equals 0. Show me that there is some c where c is in 1, 2. Show me that it exists somewhere in there. So what the intermediate value theorem says, okay, well, first of all, x to the fourth plus x minus 3 is a polynomial, so it's continuous on my interval. Okay, so we have a nice smooth function that we can draw without lifting our pencil. Okay, so first, that's the first thing. It's a continuous function. Second thing, so if I let f of x equal this, so f of x is this function, what is f at 1? F at 1, when we plug in our values, we get 1 to the fourth plus 1 minus 3, that equals negative 1. So f of 1 is negative 1. F at 2, so what happens if we plug in 2? We get 2 to the fourth plus 2 minus 3. 2 to the fourth is 16, plus 2 is 18, minus 3 is 15. Okay, so we have a situation here where f at one number, our function at one number, is negative. Our function at a different number is positive. Therefore, there must be some number between 1, x equals 1, and x equals 2, so that the function f at c is equal to 0. Right? So when you look at the intermediate value theorem, this is in this situation, a is 1 and b is 2. So the intermediate value theorem says if a is equal to 1, this is x equals 1, this is x equals 2. Our function at 1 was negative 1. Our function at 2 was 15. And this is saying that at some point it had to cross 0. So in our example, n is 0. So the intermediate value theorem says there's got to be somewhere in between x equals 1 and x equals 2 so that this function turns from negative to positive. Because it's negative at 1, it's positive at 2, therefore somewhere in between, because you can't lift your pencil, somewhere it has to be 0. This function has to be 0 somewhere in between negative 1. Or sorry, somewhere it has to be 0 somewhere between 1 and 2. If we call that number c, then c is this special number that solves this equation. Therefore, c solves x to the fourth plus x minus 3 equals 0. Right? Because c is this special place where the function equals 0. It's a special place where the function goes from a negative number to a positive number, because it has to be, by the intermediate value theorem, there has to be 1. And so we're going to call c this special number. So there has to be at least 1. So if we're doing our job properly, we also say that the reason we know this is by the intermediate value theorem. The intermediate value theorem guarantees that this happens. Again, you don't know what c is. This doesn't tell you what c value does this. It just says that there is one. That's all the intermediate value theorem does. And sometimes, in a lot of problems, that's all you need to know. That's what you want to know, whether or not there is a solution out there. And then maybe you can use some sort of sophisticated solver, like Newton's method or something else, which we'll get into later, to actually figure out what that c value is. But certainly, This just guarantees that this is actually true. Okay, and the next thing we're going to do is we're going to do some differentiation, but I think the first thing that we might want to do is take a 5-minute break. So let's come back to differentiation in about 5 minutes, and we'll pick it up there. So at about 11:45 or so, we'll get started with differentiation. Hey everybody, welcome back. So I'm just going to get started again. For those of you that are still watching, I also was able to check out the chat. A couple questions on the chat. Can you send us these notes? Is it going to be recorded? I think it's going to be recorded. I think YouTube will automatically put this up, so I'm hoping that it will be. And I'll check that afterwards. As far as the notes, I should be able to. Actually, I'm going to do that right now. I'm going to save these notes as they are, which will, I think, allow me to save all of the written examples, and then I can send them out as PDFs to everybody afterwards. For anyone that registered and I have their email address, I can send them out to you. Also, there is a place that you can post your questions. I opened up a discussion on Piazza, so if at the end of all of this you have some questions that you might want me to respond to and I might not be able to get to during the chat, and during the stream here, you can actually go into Piazza and post them, and I'll do my absolute best to get back to you certainly before your exam. So if there's something little and you want to ask a question about what I said or some step that I did in the calculation, you can put it on the chat, and I'll hopefully be able to get to it at the end of the stream if we have any time. If I'm not able to get to it, or it's a much larger question and you don't understand why this or that, you can go to the Piazza discussion board and put it up under the under my T. Wilson section, and I'll try to get to it as soon as I possibly can. Okay, so derivatives. So let's talk about derivatives before we're going to try to close up this stream by about 1. So let's see if we can get through all the questions and all the derivative stuff before 1. Okay, so if I have any function f of x and I want to evaluate it at a. The derivative of a function evaluated at a is usually denoted f prime at a. As you'll find out in future lessons and future classes, you'll probably abandon this prime notation because you'll have more than one variable. But for now, f prime at a is no problem, and we can define it as f prime of a is equal to the limit as h goes to 0 of a plus h minus f of a over h. If this limit exists. If this limit does not exist, then we say that this function is not differentiable at a. If we don't have a particular point in mind, like if we don't know where we want to take the derivative yet, we can make a more general version of the derivative and leave it as a function. And that is, instead of having an a, we just leave it as an x. And so the limit as h goes to 0 of f of x plus h minus f of x divided by x. This will allow us to calculate the derivative and then plug in the value of a after we've calculated the derivative. So we don't need to calculate this f prime at a for every single a that we want. Instead, what we can do is calculate the derivative at any x that we want, and then plug in a at the end. So this saves us a lot of work. One other thing that I want to mention is there was another version. This is the most popular version of the definition of a derivative. But another version that you might have seen before, and sometimes is okay too, is f prime at a is also defined to be the limit as x goes to a of x f of x minus f of a. Sorry. No, let's do it this way. The limit as x goes to a of, the limit as b goes to a of f at b minus f at a divided by b minus a. This is a totally cool version too if you want to use it, but it's exactly the same as the versions you see up here. Usually, and I prefer to use these two versions here. So these are the versions that I like to use, but you will see other definitions as well. They're completely equivalent, so you don't really have to worry about that too much. What are they good for? You guys have seen this before, definitely. Tangent lines and normal lines. If I have the tangent line to a curve of y equals f of x at x equals a is the line f at a plus the derivative at a, x minus a. So this is the tangent line to a curve. This is the equation of a tangent line to a curve. The equation of a normal line to a curve at x equals a is the same sort of thing, only if you look at this, this is the only thing that changes. You have a 1 over f prime at a, and you have a negative here. The reason that you have that is because, as I'm sure you're familiar from high school, you have a tangent line. The normal line is perpendicular to the tangent line, and so if the tangent line has a derivative or a slope f prime at a, the normal is the negative reciprocal, so that's why you get this difference here. So this is the formula for an equation of a tangent line and an equation of a normal line to occur. Just a quick connection between differentiability and continuity. If you know that f is differentiable at a point x equals a, then definitely we can say that f is also continuous at x equals a. So being differentiable is actually stronger than being continuous. So if you know that a function is differentiable at a, then it's also continuous at a. However, the reverse is not true. So for example, I know that if I have f of x is equal to the absolute value of x, this absolute value function is continuous. It just looks like a v. It's no problem. It's continuous at 0, but it's definitely not differentiable at 0. So there are situations where you have a nice continuous function, but it's not differentiable there. And usually when that happens is when you have points or cusps. So here is the absolute value function. You have something that comes down sharply and then goes back up. It's not differentiable here. However, it is continuous. So differentiability is stronger than continuity. Here is a very, very brief recap of a whole bunch of differentiation formulas you know and you've studied in high school already. The derivative of a constant is 0. The derivative of a power, x to the power of n. N has to be a number. I've seen a lot of people wanted to do this rule when you have a function up there, like you have x to the power of 2x plus 1 or something. This rule only works when you have the power is a number, a real number. If it's a real number, then you can do n x to the power of n minus 1. So you've seen that before. The derivative of e to the power of x is just e to the power of x. The derivative of ln x is 1 over x. Derivative of the trig functions, these are all things that you need to memorize. Derivative of sine x is cos x. Derivative of cos x is negative sine x. Derivative of tan x is secant x, and so on. So these are just a whole bunch of things that you need to memorize, and perhaps you already have from high school. So these are just all the derivative of trig functions. The derivative of log functions, the derivative of any log base a is 1 over x ln a. This includes, by the way, ln, because in ln your base is e. So the derivative, if you had ln here, this is true as well, but you just have 1 over x ln e, and the logarithm of e is 1. So you just recover the exact formula we saw up in an earlier slide for the derivative of ln x. Same with exponential functions, the derivative of a to the power of x, where a is some positive number, a to the power of x ln a. This is also true if your base is e. If you have e to the x here, you have the derivative is e to the x times ln of e, which is just 1. So what you actually end up recovering. So these are actually much more general versions, and these are very useful as well. If you need to change base for some reason in a calculation, this is a nice little change of base formula that you should memorize. Differentiable, differentiation formulas. These are kind of like limit formulas. If I have two functions that I'm adding together and I want to take their derivative, I can take their derivative separately, provided they're each separately differentiable. Just like the limit laws, these things have to kind of exist. You have to be able to do this. If you can't do that, then you're not allowed to separate them. You have to carry out the derivative with them together. Same with subtraction. So if you have two functions subtracting each other, their derivatives, you can do the derivatives independently and then subtract them. That's no problem. If you have a constant times a function, like say 7 times cos x, well, you could just take the 7 outside of the derivative and just do the derivative of cos x if you want, and that'll give you the exact same thing. Here's the product rule. So this is the first complicated kind of rule that you've seen before. If you have two functions that you're multiplying together and each of them are independently differentiable on their own, then the derivative of the product is equal to, leave one of them alone, it doesn't matter which, take the derivative of the other, plus, and then do the opposite. So leave the other one alone and then the derivative of the other. Okay, it doesn't matter which order you do these in, so you can do them in any order that you like, but the idea is take the derivative of one, leave the other one alone, and then do it the opposite way and add them together. This is the product rule. The quotient rule looks like this. If you have f of x and they're differentiable, then you can do this. So it's the bottom times the derivative of the top minus the top times the derivative of the bottom divided by the derivative, or the bottom squared. If you like the quotient rule, as anyone who was in my lecture section knows, if you like the quotient rule and you're really happy with it, then please go ahead and use it. It's totally fine. I hate the quotient rule, and in general I never use it. Instead, what I do is I rewrite anything that looks like f of x divided by g of x, I write it this way and use the chain rule, because then I have to never remember which order this goes in. However, if you want to use the quotient rule, go right on ahead. Higher order derivatives, they sound like they're more complicated, but really they're not. If you want the second derivative of something, you want the third derivative of something, that just means keep taking the derivative. So for example, in general, the nth derivative, so say n is 5, the fifth derivative of a function is equal to the derivative of the fourth derivative. So once you calculate the fourth derivative, you calculate the fifth derivative by taking the derivative again. So higher order derivatives are not that much more complicated than regular derivatives. If you want the ninth derivative of a function, take the derivative 9 times. That's all there is to it. I think I might want to try some examples before we go into the chain rule. So let's get that. So let's use the definition and calculate this function. Of course, you could use the quotient rule or my modified version if you like, but this is actually saying use the definition. So whenever they say use the definition, they mean the limit as h goes to 0, that kind of thing. So the definition says that g prime of t is equal to the limit as h goes to 0 of g t plus h minus g of t divided by h. So the first thing that most people stumble on is what is this what is g of t plus h? Well, it's actually much simpler than you could possibly imagine, and that is g of t plus h means take t plus h and stick it into your function wherever you see a t. That's simple. Just like if I had g of 3, what would you do with g of 3? You would take 3 and plug it in wherever you see a t, because that's how you do that kind of stuff. Well, this works exactly the same way. What do you do with g of t plus h? You take t plus h and stick it into your function wherever you see a t, because that's what you're supposed to do. So let's go ahead and do that. This is equal to the limit as h goes to 0 of, let's plug in t plus h wherever we see a t. And yes, it'll get messy, but that is okay. T plus h. Okay, so I plug in t plus h in that t, divided by, let's stick in t plus h in the bottom as well, 3 plus t plus h. Okay, so all I did was I took t plus h and I stuck it into my function wherever I saw t, and then when I subtract off what is g of t, well, I can just copy that down, that's no big deal. 1 over 2t times 3 plus t, and that whole thing is divided by h. Alright, so now we have some work to do. So let's stick these two things together using a common denominator. So we have the limit as h goes to 0 of, we're going to multiply the top by 3 plus t. So we have 3 plus t minus 2 t plus h, 3 plus t. Okay, so that's the first term. The second term is going to be minus 1 minus 2t times the denominator down here, 3 plus t plus h. Okay, divided by now the common denominator that we just got, 3 plus t plus h times 3 plus t. And here's where we really hope that all of our algebra skills are useful. So we're going to have to expand all of this out. And yes, I'm not looking forward to it as much as you're not looking forward to it, but let's go ahead and try it. And do it very carefully. If anyone finds an error while I'm doing this, please point it out in the chat, because I'm prone to making an error if you do these long FOIL questions, and I don't want to get too far down before realizing that I'm wrong. So this is 3 plus t, and then it's minus 2, and then let's expand this out. T times 3 is 3t. 3t plus t squared plus t squared, 3t plus t squared plus 3h plus th. Okay, so that's that first FOIL, minus this is going to be long. Oh, I guess this all should be also multiplied by 1 over h, because we still have this h on the bottom. So this is, so that's the first one, minus. So let's do this. 1 plus 3, or 1 times 3 is 3. 1 times t is t. 1 times h is h. Minus 6t. Minus 2t squared. Minus 2t squared, so that's that one. Minus 2th. Okay, so that's that FOIL. Divided by 3. Let's just actually FOIL this out. We have 9, so let's do 9 plus 3t. Thanks everyone for pointing out I forgot h. I'm going to do that right now. 9 plus 3t, 9 plus 3t plus 3t plus 3h plus t squared plus ht. I think that should be good for the bottom. And yes, I am multiplying this whole thing by 1 over h. All right. So let's see if we can clean some of this up. This is the limit as h goes to 0 of 1 over h times. All right, let's take a look at the top. 3 plus t minus 6t, right, minus 2, minus 2t squared, minus 2t squared, minus 6h. Let's see here. I'm going to get rid of this. So minus 6h minus 2ht, okay, minus 3 minus t minus h plus 6t plus 6t squared plus 2th. Yikes. All right, divided by. Let's see if anything is better on the bottom. We have a 9 plus 3t, 9 plus 6t, right, these two 3t's add together, plus 3h plus t squared plus ht. Okay, moving right along. Let's see how much this cleans up. Equals the limit as h goes to 0, 1 over h times 3. So let's see what we can do on the top. 3, let's just look at our numbers. 3 minus 3, and that's it. So all the numbers cancel out. Let's look at our powers of t. T minus 6t is minus 5t minus 6t plus 6t. So all our t's cancel out. Okay, good. Let's look at our t squareds. Minus 2t squared plus 6t squared. Okay, minus 2t squared plus 6t squared is 4t squared. And I really hope I haven't made a mistake somewhere, but okay. And then let's look at things that have h's and t's in them. Negative 2ht plus 2ht, so those cancel out, so that's nice. And now let's look at things that are just h's. Minus 6h minus 7h. That doesn't make me feel happy, but well, let's just try this. Minus 7h. Okay. I feel like my t squared should have canceled out better somewhere. Anyway, let's just carry on then. Now on the bottom, I have 9 plus 6t plus t squared. So let's do plus t squared plus 6t, t squared plus 6t plus ht plus 3h on the bottom. Okay. So this equals the limit as h goes to 0 Yeah, I'm really quite perplexed as I think this these t squared should have canceled out on the top. So let me see if I can. I'll just keep going on here and see if I can find out. Wait, so someone says I think the 6t squared needs to be 2t squared. Is this true? This would be very helpful to me. So where did so this 6t squared? Let's see if it should be yes, sorry, yeah, absolutely right. The negative becomes plus. This should not be 6t squared. Thank you very much for seeing that. This should be 2t squared. And now I don't have this 4t squared here at all. So that's good. All right, thank you very much, everybody. This is why you try to do things slowly. All right, so now I have negative 7h on the top, and on the bottom we have h times. We can factor the bottom, and the bottom factors into 3 plus, actually it just factors into what we had before, 3 plus t plus h, 3 plus t. This h cancels out with this h. And now what we get is the limit as h goes to 0 of negative 7 over 3 plus t plus h times 3 plus t times 3 plus t. And now when we take the limit as h goes to 0, this goes to 0, the h goes to 0, and you have 3 plus t on the bottom, so this answer is negative 7 over 3 plus t squared. And that's the end. So, yeah, so that's great. So hopefully on an exam or any other part in your life, you wouldn't have something that complicated, but certainly this is a situation where it's not that difficult. We just use the definition of a derivative, and we just really have to make sure that when we're doing all this FOIL stuff, that we do things carefully, because on an exam you won't have a chat telling you where you did your mistakes. So anyway, so this is this would be doing the derivative by definition, and a very complicated version of it at that. Okay, so this is probably I would hope the upper limit of what one might be asked to do on an exam. Okay, so show the function f of x minus 6 is not differentiable at 6. Okay, so how do we do this? Well, let's first remember that x minus 6 in absolute value. Let's remember what this function actually is. This is x minus 6 when x is greater than or equal to 6. And it's the negative of the version, x minus 6, when x is smaller than 6. Because when x is smaller than 6, the thing inside the absolute values is negative, so we have to take the negative of it. Okay, so let's now take a look at this function. So we can, what is the derivative? So by definition, we have the limit as x goes to 6. This is another version of the derivative. Okay, so the derivative f prime at 6 would equal this. In theory, this is the definition. And so what we have to do now is, because we kind of have this situation where this is splitting up into two different, because we're looking at the derivative at 6, and we have two different kind of functions when you get close to 6. So we need to be really careful about this, and we need to take the limit as x goes to 6 from the left and x goes to 6 from the right in order to calculate if this limit actually exists. So let's take a look at the limit as x goes to 6 from the left of f of 6, or f of x minus f of 6 divided by x minus 6. Okay, so what version of f of x, what version of the function should we be using when we have numbers that are smaller than 6? So when we have numbers that are smaller than 6, we should be using the negative version. So we should be using this version here. So this is the limit as x goes to 6 from the left of the negative version is 6 minus x right, when you actually distribute the negative there, minus the function at 6. So let's see what, when it's equal to 6, we should be using this version of the function, and when we plug in 6 into this function, we get 0. Okay, so this is 6 minus x. Okay, now this is the limit as x goes to 6 from the left, and this is -1, because when you move out a -1 out of this and then cancel the x minus 6, cancels out with the 6 minus x, and you get -1. So this limit is -1. So the limit as x goes to 6 from the left of this function is -1. So the limit as x goes to 6 from the right of this thing, of the derivative, sorry, this is not the derivative, this is the definition of the derivative. So the limit as x goes 6 from the right of this thing is equal to, well, what version of the function should we be using? Well, we're looking at 6 going to the right, from the right, so we should be using positive versions of the function, so we should be using x minus 6. So this is exactly equal to the limit as x goes to 6 from the right of x minus 6 minus the function at 6, and we've already figured out what the function at 6 is. It's 0. And this is divided by x minus 6. And if you do all that algebra, what you come up with is the limit is 1. Okay, so this is strange. The limit as x goes to 6 from the left is -1. The limit as x goes to 6 from the right is +1. So these two limits are different. Therefore, the limit as x goes to 6 of f of x minus f at 6 divided by x minus 6 does not exist. This limit as x goes to 6, this limit does not exist. And this is what the definition of the derivative at 6 is. Therefore, f prime of x does not exist. That limit that it is the definition of what the derivative is does not exist at x equals 6. Therefore, f of x is not differentiable at 6, which is exactly what they wanted us to show. Right? Show the function is not differentiable at 6. Okay, but again, the whole idea of this is one of the definitions of a derivative. This is the definition of a derivative at x equals 6, and what we ended up showing is that this limit doesn't exist because the limit is different from the left and the right of 6. So therefore, because this limit doesn't exist, the derivative can't exist because this is the definition of what a derivative is, and it doesn't exist. So the derivative does not exist at 6, which means by definition it's not differentiable at 6. Okay, so let's move along to something that we would want to take the derivative of. So let's differentiate f of y. So here what they mean is they want f prime at y. So that's the derivative of f. I know it kind of looks weird that we're taking the derivative with respect to y, but in theory we can take the derivative of any variable we want. F is a function of y, so we can figure out what the rate of change of f is with respect to y. That's no problem. And so now we have one function here that is a function of y, and we have it multiplying another function here, which is a function of y. So this would be a product rule. Right, one function times another function, so we need to use the product rule. So I'm going to rewrite these as y. Before I do that, I want to say that this is the derivative with respect to y of the following: y to the -2, because that's what this is, minus 3y to the -4 times y plus 5y cubed. Okay, so this is the product rule, so I'm going to leave the first thing alone, y minus 2 minus 3y minus 4, and I'm going to take the derivative of the second thing, y plus 5y cubed. So this is the product rule, plus, leave the second thing alone, y plus 5y cubed times the derivative of y minus to the -2 minus 3y to the -4. Okay, so now it's just a matter of calculation. So this equals y to the negative 2 minus 3y to the negative 4 times the derivative of this. This is pretty easy stuff. This is just the derivative of y with respect to y is 1. The derivative of 5y to the power of 3, you move the 3 down, and it becomes 15y to the, subtract 1 off from the 3, 15y squared. Oops, I'm just making things worse. 15y squared plus, let's leave this alone, y plus 5y cubed. Now we're going to take the derivative of this thing. The negative 2 comes down, becomes negative 2y to the power of negative 3, because negative 2 minus 1 is negative 3. This negative 4 comes down and multiplies this negative 3, so I get 12 plus 12y to the negative 5. And that's it. And if you really wanted to clean that up, I suppose you can. But this is certainly the derivative, and in some cases, people like you to leave it non-simplified because they can really see what you've done. As soon as you write the next line, you're going to simplify things different than I would, different than your friend would, so it gets really complicated to see whether or not you have the right answer. Also, so I would say on an exam or whatever, simplify things if they're very easy to simplify. Like if you have 3x minus 2x, I would simplify that to x. But if you have something long and complicated in this, maybe you should just leave it alone, and that should be fine. Okay, so that's the derivative. Okay, now something a little bit non-traditional. Suppose that I know that the function of the value at f, the value of f when you plug in 5 is equal to 1. The derivative at 5 of f is 6. G at 5 is negative 3, and g prime at 5 is 2. Find the following values: the derivative of fg at 5, the derivative of f divided by g, and the derivative of g divided by f. Okay, so we can actually do these just knowing the product and quotient rules without even knowing what these functions are. So fg prime at 5 by the product rule is f at 5 times g prime at 5 plus g at 5, so leave the other one alone, times f prime at 5. F at 5 is 1. G prime at 5 is 2, so 1 times 2, plus g at 5 is negative 3, times f prime at 5 is 6. So this becomes 2 plus negative 18, so this becomes negative 16. So I've done everything correct. B, now I want the derivative of f divided by g prime at 5. So the derivative of this kind of quotient looking thing. So yeah, in this case we might as well use the quotient rule. So this is where I have to remind myself what the quotient rule looks like. So if I remember correctly, it is the bottom times the derivative of the top. So g at 5, the bottom times the derivative of the top, f prime at 5, minus the top, f at 5, times the derivative of the bottom, g prime at 5, divided by the bottom squared, which is g at 5 squared. So I can go ahead and do that. G at 5 is negative 3. So this should be negative 3. The derivative of f at 5 is 6. Minus f at 5, which is 1. Times the derivative of g at 5, which is 2. I should divide by g at 5 squared. What is g at 5? Where'd it go? Negative 3 squared. So if we add all of this up, you have negative 18 minus 2, that's negative 20, divided by 9. Okay, moving along. C, g over f prime at 5. Same kind of thing. Let's use the quotient rule. So this becomes the bottom, f at 5, times the derivative of top, g prime at 5, minus the top, g at 5, times the derivative of the bottom, f prime at 5, divided by the bottom squared, which is f at 5 squared. Okay, so f at 5 is 1. G prime at 5 is 2. Minus g at 5, which is negative 3. f prime at 5 is 6 divided by f at 5 squared. F at 5 is 1, so this is 1 squared. So when you work this out, you have 2 plus 18 is 20 divided by 1. So this answer is 20. Okay, so just a different kind of take on product rule. So yeah, you certainly should be good at using the product rule as we did in the example before, but also you can use the product rule to figure out things like this, even if they don't give you the functions. All right, so find out points on the curve y equals 2x cubed plus 3x squared and minus 12x plus 1 where the tangent is horizontal. So something I didn't really mention in the notes, but I think everyone knows by now, the slope of a tangent line to a function, to, let's say, to f of x at x equals a is precisely equal to the derivative of f at a. So this is something that everyone, I'm sure, remembers from high school. So here we have a curve. So for us, f of x is equal to 2x cubed plus 3x squared minus 12x plus 1. And so what we would like to know is where is the slope of this tangent line horizontal? So at what values of x is the slope of the tangent line 0? Okay, horizontal means slope is equal to 0, right? The slope is flat. It's a flat line. So let's figure out where this happens. The derivative of f is 6x squared. 3 comes down to make it 6, and you have x squared, plus the 2 comes down to make it 6, plus 6x minus 12. And we would like to, we want to know when this f prime of x equals 0. So we would like to know when the slope is 0. Okay, so let's figure that out. We want that, so 6x squared plus 6x minus 12 is equal to 0. What we can do is we can factor this out. 6x squared plus x minus 2 is equal to 0. We can factor that, and we get 6x plus 2, x minus 1 is equal to 0. And so the only way to make an equation that looks like this, where you have 3 things multiplying each other, the only way we can make this equal to 0 is if one of these things is equal to 0. So that will happen if 6 is equal to 0. That's never going to happen, so that's impossible. If x plus 2 is equal to 0, so x plus 2 equals 0 would mean that x is equal to negative 2. And x minus 1 is equal to 0 means that x is equal to 1. So that means x equals negative 2 or 1. So the slope of the tangent line is horizontal. Tangent line horizontal when x equals negative 2 or x equals 1. Good. All right. So that's pretty good. All right, so now something maybe a little bit more tricky. For what values of a and b is the line 2x plus y equals b tangent to the parabola y equals ax squared when x equals 2? All right, so what values of a and b is the line 2x plus y equals b tangent to the parabola y equals ax squared when x equals 2? Okay, so the first thing is tangent to the parabola. So this is a line. So this is so essentially what it's saying is this is the tangent line to this parabola. So we would like to know what values of a and b make this the tangent line to this parabola when x equals 2. So the first thing we might need to know is what is the slope of any tangent line? Slope of any tangent line to our function y equals ax squared. And we calculate that exactly as we did before. It's the derivative f prime at x equals 2ax. So f prime at 2. So the slope of any tangent line to this parabola when x equals 2 is 2a times 2 is 4a. So if I have any parabola that looks like y equals a times x squared, any parabola that looks like that, the slope of its tangent line at 2 is equal to 4a. Now look at our tangent line. They said they want the tangent line to be this. So if we rearrange this, this is y equals negative 2x plus b. Right? We can see what they want the slope to be. They want the slope to be negative 2. So they want f prime at 2 to equal negative 2, which means negative 2, the slope that they want, and the slope of any parabola that looks like this is negative 2 has to equal 4a, which means a has to be equal to negative 1/2. All right, so we know what a is. So now we know that the parabola, our parabola, is exactly the parabola negative 1/2 x squared. So now we have a specific parabola that we're dealing with. So if the only thing left that we have to figure out is, so we know what a is, now the only thing that we have to figure out is what b is. And if we want to know what b is, what we can do then is, if this is the slope of the tangent line, or this is the equation of the tangent line that they want, y equals minus 2x plus 6, this equation of the line must also go through the point that they want the tangent line to come from, right? So when x equals 2, when x equals 2 is on our parabola is negative 1/2 times 4, which is negative 2. So the point 2, negative 2 is the point on the parabola that our tangent line goes through. Certainly they said x is equal to 2. That's where they want the tangent line to go through. But now we need to figure out what is the y value? What point on the parabola is x equals 2? Well, now that we know what the parabola looks like, we can actually find the point on the parabola that this happens at. The point on the parabola is 2, negative 2. So now that we have an x value and a y value, and this line goes through this point, we can easily plug this in to figure out what b is. So we have 2, what's our x value? 2, plus what's our y value at this point? Negative 2, has to equal b. So in this case, b has to be equal to 2. Because we have 4 minus 2 is equal to b, which means b is equal to 2. Okay, so let me just recap that question again. They wanted to know the values of a and b so that this line is tangent to this parabola at x equals 2. So the first thing we had to figure out is what parabola are they talking about? We don't know what a is. So what we did was we said, well, if I know any parabola that looks like this, its derivative is this. So the slope of any tangent line of a parabola that looks like this is this. And they want it when x equals 2. So we know that the parabola, or the slope of the tangent line there would be 4a. Well, they said that they want this to be the tangent line. This tangent line has a slope of negative 2. So that allowed us to compare our slope of the tangent line to the one that they wanted, and we concluded that a equals negative 1/2. So now we have a specific parabola that we have in mind. So then we could figure out what the point on the parabola this tangent line is going through. So because they want x to equal 2, we can plug that into our actual honest to goodness parabola to figure out the point on the parabola this tangent line is going through. So this tangent line is going through 2, negative 2. So once I know a tangent line is going through 2, negative 2, I can just plug in 2 for x, negative 2 for y, and I can solve for b, which is what I did. B equals 2. Okay, so just kind of a little twist on tangent lines and derivatives. Let me see if I want to go over. So I want to save these again, just to make sure that nothing gets left out. Chain rule. Actually, before we get into chain rule, let's do this question here, because I don't think it needs the chain rule. All right. So you might be inclined first to say this is a limit question, so maybe I should factor it, and you can factor it if you want. I don't want to. I want to show you a kind of a different way that's kind of a sneaky trick. And the other thing is you might want to use L'Hopital's rule. We're not here for that, because as x goes to 1, this goes to 1, the top goes 0, bottom goes 0. Okay, maybe use L'Hopital's rule. However, just a little sneaky trick that we could take a look at this. So if I have a function, if I let f of x equal, say, x to the power of 1,000, then its derivative, by definition, f prime of x is the limit, f prime at, the derivative of this function at 1, f prime at 1, by definition is my function minus f at 1 over x minus 1, the limit as x goes to 1. This is the derivative of my function at x equals 1. And if I look at this, this looks very familiar. This is limit as x goes to 1 of, what is my function? X to the power of 1,000. Minus what is my function at 1? When I plug in 1 into this, 1 to the power of 1,000 is 1 divided by x minus 1. This is what they want. They want this. This is what it's actually equal to, the derivative at 1. So rather than go through some contortions with L'Hopital's rule or some factoring, the thing that they want is exactly equal to the derivative of my function at 1. So let's just calculate the derivative really, really quickly. The derivative of this function is 1,000 x to the power of 999. The derivative at 1 is equal to, plug in 1, and you get 1,000. So the limit as x goes to 1 of the thing that they wanted, 1 x to the power of 1,000 minus 1 over x minus 1 is equal to 1,000. Because I was able to rewrite the limit that they wanted as a derivative of some fancy function that I came up with. So then I could just figure out the derivative at 1, and it gives me exactly what they wanted. So this is an example of actually doing it backwards. So they give you a limit, and you turn it into a derivative and calculate the limit that way. So this is something to keep in mind as well. Of course, I'm sure if you use L'Hopital's rule, you'd come to the same conclusion, but sometimes you can't use L'Hopital's rule, so it is good to have this kind of thing in mind. Keep in mind that sometimes when they ask for a limit, what they're actually asking for is the derivative of something. All right, so now is where we definitely need the chain rule. So there's a chain rule question, but let's talk about the chain rule really, really quickly. All right, chain rule. So the chain rule looks really confusing when you write it down, but when you actually do it, it's actually not as confusing. If you have a function that is a function stuck in another function, so if I have a function that is like this, f of g of x, and I would like to know what the derivative of this thing is. The way to do that is to take the derivative of the outside function, take the derivative of f. I guess I used h here, so let me just use h. Probably better to stay consistent. If I have the function h of x stuck inside the function f of x, and I want to know its derivative, the derivative of this whole thing is the derivative of, okay, I see what I did. Right, this function f of x is, okay, I'm going to just rewrite it this way. This function f of x, the thing that I want the derivative of is a function g of x when I stuck h of x inside. And so the way to calculate this is the derivative of the outside function, g, times the derivative of the inside function, h. That's really all there is to it. And the more times you use the chain rule, the easier and easier it gets. So let me give you an example. Pretty simple example. So for example, if f of x was equal to something like cos x squared plus 7x, okay, in this situation, g of x would be cos x, right? That's the outside function. That's the thing that I'm sticking things into. And the inside function, h of x, would be equal to x squared plus 7x. It's the function I stuck into cos x. So my derivative by the chain rule is the derivative of the outside function. So what's the derivative of cos x? Negative sine x. But I need to make sure that I keep the inside there. So okay, so just the derivative of cos times the derivative of the inside function. So what's the derivative of the inside function? The derivative of the inside function is 2x plus 7. Okay, so the chain rule really is just take the derivative of the outside function and then multiply by the derivative of the inside function. Sometimes the inside function itself will need the chain rule, and then you just keep chaining it out and doing more and more. Take the derivative of the outside, multiply by the inside, etc. Okay, so here's a situation where we have some function, capital F of x is equal to f of g of x. So this is exactly pretty much the same thing that we were just looking at. And they would like to know, what is f prime at 5? Well, f prime at 5 is exactly equal to, by the chain rule, f prime at g of 5 times the derivative of the inside, g prime at 5. Okay, so this is the derivative of, what is g at 5? G at 5 they give us is negative 2, times the derivative of g at 5, g prime at 5 is 6, so this is times 6. The derivative of f at negative 2 is 8. Wait a minute. Sorry, that's the function at negative 2. The derivative at negative 2 is 4 times 6, so this ends up being 24. Okay. So this is another example where you can actually do the chain rule, just like we did the product rule and stuff, without actually knowing what the function is, just by using what the definition of the chain rule is. The chain rule says if I want the derivative of this master function, which is just g stuck inside of little f, what I need to do is take the derivative of the outside function, evaluate it at the inside function at 5, times the derivative of the inside function at 5. And so they give us all the information we need. G at 5 is negative 2. The derivative of f at negative 2 is 4. And the derivative of g at 5 is 6. So that works out to be 24. Okay, just a simple little use of the chain rule. All right, moving along. About 20 minutes left, so hopefully we can get through the rest of this. Should be no problem. Implicit differentiation. So there's a lot of confusion about implicit differentiation and when you should use it and when you when you shouldn't. You can technically use implicit differentiation whenever you want. You can always use implicit differentiation. It's just sometimes you don't need to. And what is the difference? You wouldn't need to use implicit differentiation if I said, say y is equal to 90x plus sine of x squared, say. Because this is telling me exactly what the relationship between y and x is. Y is exactly equal to this. So I would take dy by dx, and I would go on using the chain rule or product rule, no problem. Because y is explicitly given as a function of x. They say this is exactly how y and x are related. However, in the real world, things aren't always that clear cut. Sometimes you have a situation like this. In this situation, they are defining y as a function of x. Y is related to x. It's just very convoluted as to how these two things are related. So how are we going to calculate the derivative of something that looks like this, where all the y's and x's are jumbled up together? There's two ways you could possibly do it. The first would be maybe you could isolate for y. Maybe you could actually turn it back into something that looks like this and go about your regular differentiation. That would be no problem. However, if you were given something else like this and you were asked to isolate y, that might be impossible. It probably actually is. So isolating for y and then differentiating is not going to help us in this situation. So we need to figure out a different way to do this. And the way to do this is called implicit differentiation. And the reason it's called implicit, the reason they use the word implicit, is because y is given as a function of x implicitly by this. They're not giving it explicit, like y is equal to this thing. They're implicitly giving a relationship between x and y. Okay, so how do we do implicit differentiation? We differentiate both sides of the equation, and we have to remember that y is a function of x. We always have to remember that y is a function of x. So For example, cos y needs the chain rule because y is a function of x. It's y of x stuck inside cos of x. So this is y of x inside cos of x. So we have to remember when we differentiate things that look like this, that y is a function of x and we need to use the chain rule. Once we've taken all our derivatives of both sides, then we just isolate for dy by dx. Okay, so let's try doing one of those. Trying to do a maybe more of a complicated example. So let's figure out what dy, the derivative of y with respect to x in this situation is. Again, maybe you want to try isolate y in this situation and then do your regular differentiation. In general, I'll bet you it's impossible, so you don't really want to do that. So instead what we're going to do is we're going to use implicit differentiation. So step 1, take the derivative of both sides of this with respect to x. So the derivative of tan x over y is equal to the derivative of x plus y. Okay, no problem. The derivative of x plus y is pretty easy. The derivative of x with respect to x, everybody knows, is 1. The derivative of y with respect to x is precisely what we're looking for, dy by dx. It's the derivative of y with respect to x. Over here, a little bit more complicated. This is a function x divided by another function of x inside a function of x, inside of tan. So we need to use the chain rule here. So after what we just learned about the chain rule, we take the derivative of the outside function. The derivative of tan is secant squared x over y. So that's the derivative of the outside function times the derivative with respect to x of the inside function, which is x y to the negative 1. I'm just going to write it that way. I didn't change anything. I just, instead of writing it x over y, I did x times y to the negative 1. It's just going to be easier for me to deal with. I mean, you could use the quotient rule here. I'm not going to. Okay, so I'll just rewrite that. Secant squared x over y times, now let's take this derivative. This is a product rule. X is a function of x, obviously, and y is also a function of x. So this is a function of x times a function of x. So we need to use the product rule here. So let's take the derivative of the first one and leave the second one alone. That's just y to the negative 1, because the derivative of x with respect to x is just 1. Plus, let's leave the first one alone, x, and now let's take the derivative of this. So we need to take the derivative of y. So we take the derivative of y with respect to y. So we get negative 1, y to the negative 2. So that's the derivative of the quote-unquote outside function. Then we need to multiply by dy by dx. Okay. So the derivative of y to the power of negative 1 is, bring the negative 1 down, subtract off 1 from the exponent, negative 2, and then you still need to multiply by dy by dx, because that's the derivative, that's the complete derivative of y to the negative 1 with respect to x. That's the chain rule. On the right hand side just stays dy by dx, no big deal. Okay, so this is, let me see if I can expand this all out. This is y to the negative 1, secant squared. So that's step 1. Okay, we're done our derivative. So step 2. Now we need to isolate dy by dx, because that's what they're looking for. They're looking for dy by dx. So let's isolate dy by dx. So let's first just expand this out. And for those of you that really don't like dy by dx because it makes you uncomfortable to solve for dy by dx, this is just like a parameter. Imagine this was just a big capital A here, or a big capital B or something, and you're just isolating for dy by dx. So use all the techniques that you learned in high school, how to isolate for a variable. We're isolating dy by dx. We're solving for dy by dx. So you can use all the methods that you know. So for example, I'm just going to expand this all out. Okay, so this becomes minus xy to the negative 2 dy by dx times secant squared x over y. And on the right hand side we have 1 plus dy by dx. So if I was asking you to isolate for dy by dx, what do you normally do to isolate things? You put everything that you're trying to isolate on one side and everything that doesn't have that thing on the other side of an equation. So let's move everything with dy by dx to the right hand side, everything that doesn't have a dy by dx to the left hand side. So this is y to the negative 1 secant squared x over y. Fine. So that's on that side. This has a dy by dx, so I'm going to leave it there, minus 1. That comes along the other side, and that is equal to, I'm going to move everything that has a dy by dx to the right hand side. So I have dy by dx plus, okay, so that's that dy by dx. Now I'm going to move this big term over to the other side. X, y to the negative 2, secant squared y over x times dy by dx. Okay, so just like any other thing, if you were isolating for dy by dx, what we could do is we'll rewrite the left-hand side. Secant squared x over y minus 1. And the right-hand side, we're going to factor out a dy by dx out of everything. So we have a dy by dx, 1 plus, when we factor out the dy by dx, what do we have here? X, y to the negative 2, secant squared y over x. Make those square brackets. And now we just divide both sides by this big thing on the right hand side. We're just isolating for dy by dx. So dy by dx equals this thing, y minus 1, secant squared x over y minus 1. That's the left hand side divided by, what did we divide both sides by? This, 1 plus x, y to the negative 2, secant squared y over x. And that's it. That's the derivative of y with respect to x. And yes, I mean, I guess you could, if you want to, you know, get a common denominator and solve that way. But for now, we'll just leave it like that. Let me see. Someone just said, is it y over x? Or x over y? Y over x on the left. On the right. Okay, so people are saying that they think it's wrong. So yeah, so to Aaron Schulman, yes, it will be recorded, or I think it's being recorded. But let me see. Shouldn't it be on the secant squared x over y? So let me see, secant squared x minus y divided by dx. Secant squared, let me see, secant squared so on the left the 1 comes over, that goes over there. Sorry, x over y, sorry, yeah, I gotcha. All right, yes, here this should be, thank you very much. So this should be x over y, x over y. I think that's what everybody's talking about. And so this should be x, oops. Yeah, I just wrote that down wrong. That's all. Sorry. Yeah, so it should be x over y. So thank you very much for all you fine people who know how to do this better than I do. So there you go. X over y. Okay, so I think that that's good for an implicit differentiation. And now let's do, I think this is the second last question we have to do, so we'll do this quickly. And it's kind of a neat little application of implicit differentiation. Before we kind of, I think implicit differentiation was the last note. Nope. We'll talk about logarithmic, and then we'll be done. Then we'll take a break for lunch. All right, so consider a lamp located 3 units to the right of the y-axis and a shadow created by an elliptical region x squared plus 4y squared less than or equal to 5. If the point negative 5, 0 is on the edge of the shadow, how far above the x-axis is the lamp located? So this seems like a very complicated problem, but once you kind of draw it, it starts to make sense. Here is the xy axis, so we have a lamp. There's a lamp located 3 units to the right of the y-axis, so here's a lamp. Okay, so there's a very tall and skinny lamp. It's at 3. And it has a height. I don't know what its height is. And it has a shadow. So there's a light coming from this. And there's an ellipse. X squared plus 4y squared is less than or equal to 5. So you don't really need to know too much about what an ellipse looks like. But for our drawing, let's just draw it in. So here's a very poorly drawn ellipse. And so I guess you have some object here, and then you have a light shining down here, and then this light, oops, this light is coming down, hitting there, going like this, and then this light is coming down, oops, like this, hitting there, going like that. Okay, this is crossing. It says that if the point -5, 0 is on the edge of the shadow, so here is the shadow, this is the shadow. This point is on the edge of the shadow, so this point here is -5, 0. Okay, the question is, what should h be? This is the question. Okay, so how are we going to solve this? So, the first thing we're going to notice is that this shadow, we can look at it this way. This shadow is, this line of this shadow is a tangent line to this ellipse. I know it doesn't look like a tangent line, but it's a tangent line to this ellipse at that point, and we'll call that point AB. Okay, so this comes from here all the way down, hits this in a tangent way, just scrapes the edge of the ellipse, keeps going, and it crosses the x-axis at -5, 0. And so the question is, how high is h? So what we're going to the game plan is going to be figure out what the slope of this tangent line is, and go all the way back, figure out what this tangent line is, and figure out what the value of h is essentially at x equals 3. So this is what we're going to do. All right, so we would like to know the slope of this tangent line. The tangent line, the slope of any tangent line is the derivative of the function that it's tangent to. So the function that it's tangent to is this, x squared plus 4y squared equals 5. So we have x squared plus 4y squared equals 5. That's this curve, right? Just the curve, just what the actual ellipse is. This less than or equal to means that you're talking about a region inside the ellipse. But the curve that is on the outside, the curve that actually defines this ellipse, is just the curve x squared plus 4y squared equals 5. Okay, so here's the question. Let's figure out the tangent line to this ellipse at the point AB. So let's figure out what the tangent, let's figure out the tangent line of this. So we would like to know what dy by dx is. So we're going to take dy by dx of both sides of x squared plus 4y squared equals the derivative d by dx of 5. So let's do that derivative. And what we end up with is 2x, because the derivative of x squared is 2x, plus 8y, so that 2 comes down and makes a derivative, times dy by dx by the chain rule. Okay, whenever we take a derivative whenever we take a derivative of y, we need to make sure we multiply by dy by dx. The derivative on the on the right hand side is just 0. So if we solve for this, dy by dx is equal to this 2x comes over, -2x, and then we divide by 8y, and what we end up with is that this derivative is -x divided by 4y. So you give me a point xy somewhere on that ellipse, and I'll tell you what the slope of the tangent line is at that location. Specifically, at this point AB, at this point on the ellipse, the slope of the tangent, let's do this, slope of the tangent equals -a over 4b. So let's just keep that in mind. Okay, if I'm talking about this point here, this is the slope of any tangent line on that ellipse. At the point AB, this is what it is. Okay, so the next thing that I would like to know is, if I take a look at this this point way up here is 3, h. Okay, so this line that's joining these 2 points, okay, has a slope. We already calculated the slope. It's -4 or -a over 4b, because that's the slope of the tangent line there. But we can also calculate the slope of this line by knowing that this is a point on the line, this is a point on the line, so we can do rise over run. So the slope, slope is equal to rise over run, so h minus 0 divided by 3 minus -5. So So this is h over 8. Okay, so we know that the slope of the tangent line is h over 8. And we also happen to know that the slope of the tangent line is supposed to be negative a over 4b. So what we can also look at is that slope also has to be the same as, let's take a look at this, it's also this slope of this line here, because it's all the same line. So the slope of this big line going between this point at the lamp and this point here is equal to the slope of the tangent line, which we calculated, which is also equal to the slope of this little piece here. So we can actually do the same thing here. The slope of this little piece of the slope of the line is b minus 0 divided by a minus negative 5. So just a little piece, we can also calculate the slope here as b minus 0 over a minus negative 5. So that is equal to b over a minus 5. So all of these three things have to be the same number. Okay, so what we're going to do now is, because these two things have to be the same number, we're going to figure out a relationship between a and b. So negative a over 4b, which is what we calculate the slope of the tangent line to be using our derivative, that has to be equal to b over a minus 5, because rise over run. So if we actually calculate this, we have that multiply both sides by a over 5, and we have negative a squared plus 5a is equal to 4b, multiply both sides by 4b, we get 4b squared, which means that 4b squared has to be equal to negative a squared plus 5a. Okay, but we know that the point AB is on the ellipse. So AB is on the ellipse, which means we know that if we go up to the equation of ellipse, a squared plus 4b squared has got to be equal to 5. A squared plus 4b squared has got to be equal to 5, because our point AB is on that ellipse. A plus 5, okay, so everyone's saying a plus 5. Yeah, thank you. A minus 5 is, thank you very much, a plus 5, so that changes that to a plus 5, which means that changes this to a squared is negative a squared minus 5a, which means, okay, so that's fine. So because we know from our slope stuff that 4b squared has got to be equal to negative a squared minus 5a, we can plug in this 4b squared for that 4b squared, and we know that a squared plus negative a squared minus 5a has got to be equal to 5. That a squared cancels out with that a squared, and you get negative 5a has got to be equal to 5, which means a has got to be equal to negative 1. And if we go back up and check this, if we go back in and put in a equals negative 1, what we end up with also is b is equal to 1. All right, now with that sort of information, now we can go back up and realize that here we have the slope with h in it, and we can actually calculate the slope from either of these two formulas. So I'm running out of space here, but we know that h over 8 is equal to b is 1, a is negative 1 plus 5, so that is 1 over 4, which means that when you multiply the 8 up, h has got to be equal to 2. So the height of the lamp is 2. So again, just thank you very much for everyone pointing out my little error. But at the end of the day, what is this? This is just a question about tangent lines. So you calculate the slope of the tangent line by finding the derivative, but you also can calculate the slope of this line by connecting any of these points. So understanding the relationship between the slope of the tangent line and the slope between 2 points is what ends up allowing us to solve this equation, or solve this question. Okay. So one more example, and then just a quick slide about logarithmic differentiation, then we'll take a break. So just like we saw before, actually maybe I'll leave this for everyone to do. Maybe I'll leave it for everyone to do. So the trick is to this question, just like we saw before, we've already done an example like this. Turn this a derivative. Okay, so find some function so that when you say what is f prime of x, it's some limit, and what you end up getting is this. So what you end up getting is the limit as, so find me some function so that the limit as h goes to 0 of the fourth root of 16 plus h minus 2 over h. Find me some function that does this so that the derivative is equal to this, and then you can figure out what that limit is. Okay, so that was the last kind of question, but I did want to just remind you, we didn't do any question like this of logarithmic differentiation. The idea behind logarithmic differentiation is sometimes it's beneficial to take the log of both sides of a function before you take its derivative. So then you take the log of both sides, and then you do the derivative of both sides, and you use implicit differentiation. So logarithmic differentiation is nothing very fancy, except before you even get started, you take the logarithm of both sides, then you do implicit differentiation. So this is all implicit. And this is the log part. You just take the log of both sides, use implicit differentiation, and then you're done. Okay, and then these are just formulas for you to memorize. Derivatives of inverse trig functions, you should have these memorized. Derivatives of inverse functions has a formula like this. Okay, so let's take a break. The next session starts at 2 o'clock, and it is applications of derivatives. So things like related rates, L'Hopital's rule, all that kind of fun stuff. And again, if you have any questions, post them on, you can go into Piazza, and there's an area there. I've posted a place that you can post questions if you have any. I won't probably be able to get to them before the end of today because I have 2 more sessions to do, but hopefully I'll be able to get to them eventually. So if you have any questions, put them on there. And thank you everyone for watching, and I will hope to see everybody at 2 o'clock.